You've probably looked up at the night sky and felt like you could see exactly where your home in space begins and ends. That bright band of the Milky Way seems to have clear boundaries, like a river flowing across darkness. But what if everything you think you know about the edges of our galaxy is wrong? For centuries, scientists believed they understood the limits of our cosmic neighborhood. They drew neat diagrams with definite borders and confident measurements. Yet each new discovery has shattered these assumptions, revealing that reality is far stranger and more mysterious than anyone imagined. The edges we thought we could trace simply dissolve when examined closely, replaced by something much more fluid and interconnected. In this video, we'll explore how far our galaxy actually reaches and discover why the answer might surprise you more than you expect. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too, just like you did. Thank you. Now, let's get started. Picture yourself looking up at the night sky. From somewhere far from city lights, that faint, misty band stretching overhead. That's our galaxy seen from the inside. We're sitting inside this massive structure, trying to figure out its shape and size, like standing in the middle of a forest and wondering how far the trees extend. The Milky Way contains hundreds of billions of stars, each one a sun, many with their own planets, all bound together by gravity into this sprawling cosmic city. But unlike a real city, there's no clear border, no fence marking where it ends. Instead, it just gradually fades away, becoming thinner and thinner until it blends into the emptiness between galaxies. We live in what you might call the suburbs of our galaxy, about 27,000 light years from the center. Light years from the center. That's a comfortable distance, not too crowded, not too isolated. A light year, by the way, is nearly 10 trillion kilometers. The distance light travels in a full year. When we talk about galactic distances, we're dealing with numbers that stretch the imagination. The main disk of the Milky Way spans about 100,000 light years from edge to edge. Even traveling at light speed, it would take you 100,000 years to cross it. That's just the bright part though, the part that shows up in those beautiful spiral galaxy photos you've probably seen. But galaxies are like icebergs. Most of their mass lies hidden. Beyond the visible disk, there's a vast halo of stars, gas, and something called dark matter. This halo can extend several 100,000 light years further out. Dark matter is one of those cosmic mysteries. We can't see it directly, but we know it's there because of how it affects the motion of stars and gas. This raises a philosophical question that astronomers grapple with. When does the Milky Way stop being the Milky Way? Is it where the last recognizable star appears, or where our galaxy's gravitational influence finally gives way to that of our neighbors? The answer isn't straightforward. Imagine Earth's atmosphere. It doesn't suddenly end at some invisible ceiling. Instead, it gradually thins as you go higher, eventually becoming indistinguishable from the vacuum of space. Our galaxy works similarly. The density of stars and matter slowly decreases as you move outward. Recent discoveries have made this picture even more complex. Astronomers have found streams of stars torn from smaller galaxies that wandered too close to the Milky Way. These stellar streams can stretch for thousands of light years, like cosmic ribbons wrapped around our galaxy. They're the remnants of ancient collisions, evidence that galaxies grow by consuming their smaller neighbors. We also have companion galaxies. The Large and Small Magellanic Clouds are two irregular galaxies that orbit us. They're visible from the southern hemisphere as fuzzy patches of light. But even these raise questions about boundaries. Are they part of the Milky Way system, or separate entities that just happen to be nearby? For most of human history, people thought the Milky Way was the entire universe. Those fuzzy patches of light that astronomers called nebulae, they were assumed to be clouds of gas within our own galaxy. It wasn't until the 1920s that we realized many of these nebulae were actually other galaxies, incredibly distant islands of stars. This discovery transformed our understanding of cosmic scale. Suddenly, our galaxy went from being everything to being just one among billions. It was both humbling and awe-inspiring. We learned that the universe is far larger and more populated than anyone had imagined. But this revelation also sharpened the question of our galaxy's boundaries. If there are other galaxies out there, where does ours end and the space between them begin? The answer involves understanding the sphere of gravitational influence around our galaxy. Beyond a certain distance, other galaxies start to have more pull than the Milky Way does. Our nearest large neighbor is the Andromeda Galaxy. It's about 2.5 million light-years away. That might sound like a safe distance, but in cosmic terms, it's practically next door. In fact, Andromeda is slowly moving toward us. In about 4.5 billion years, the two galaxies will collide and merge. Don't worry though, galaxy collisions aren't the catastrophic crashes you might imagine. The distances between stars are so vast that most would simply pass by each other. It would be more like two swarms of fireflies interpenetrating than two solid objects smashing together. This future merger highlights something important about galactic boundaries. They're not permanent. Galaxies grow, change, and sometimes combine. The Milky Way we see today is different from what it was billions of years ago, and different from what it will become. Measuring galactic distances requires clever techniques. Astronomers use various types of standard candles, stars whose brightness we can predict. By comparing their actual brightness to how bright they appear from Earth, we can calculate their distance. Variable stars called Cepheids pulse with a rhythm that reveals their true luminosity. Type 1a supernovas all explode with roughly the same energy, making them excellent distance markers. But even with these tools, mapping our galaxy is challenging. Dust clouds block our view in many directions. The galactic center, for instance, is completely hidden behind thick lanes of cosmic dust. We can only study it using infrared light, radio waves, and other radiation that can penetrate the obscuring material. The rotation of our galaxy also complicates measurements. Stars closer to the center orbit faster than those farther out, but not in the simple way you might expect. The outer regions rotate surprisingly quickly, which is part of the evidence for dark matter. Without this invisible mass providing extra gravitational pull, the outer stars should be moving much slower. All these complexities mean that defining the edge of our galaxy isn't just a matter of looking farther out. It requires understanding the physics of how galaxies form, evolve, and interact with their environment. Modern estimates suggest that including the dark matter halo, the Milky Way might extend as far as 600,000 light-years from its center. But even that number comes with uncertainties. As our instruments become more sensitive, we keep finding fainter and more distant structures associated with our galaxy. Each new discovery pushes the boundaries a little farther out, reminding us that the universe still holds surprises. Perhaps the most profound aspect of studying galactic boundaries is what it reveals about our place in the cosmos. We're residents of a vast, dynamic system that's constantly changing and growing. Our galaxy isn't a static backdrop, but an active participant in the cosmic dance of matter and energy that has been unfolding for billions of years. Picture a galaxy like layers of an onion, each one made of different materials, each contributing something unique to the whole structure. The disk holds stars, gas, dust, all arranged in those graceful spiral arms we see in photographs. Move inward, and you find the bulge, where stars pack together densely around a massive black hole at the very center. Drift outward, and there's the halo, filled with ancient star clusters, and that mysterious, invisible matter we can only detect through its gravitational effects. None of these regions have sharp edges, no clear line where one stops and another begins. Galaxies aren't neat packages with definite borders. They're sprawling, dynamic systems that fade gradually into the darkness between stars. When we ask how far our galaxy reaches, we're really asking how far our cosmic home extends, and the answer depends on which layer we're talking about. There's something deeply comforting about this uncertainty, this gentle blurring of boundaries. It mirrors how we think about home here on Earth, doesn't it? Home can mean your bedroom, your house, your neighborhood, your city, expanding outward in concentric circles of belonging. In space, that same layered concept applies, just on scales that stretch the imagination. Most people have that moment, that shift in perspective, when they first understand what that pale band of light across the night sky really is. It's not decoration, not some distant phenomenon. It's the cross-section of our own galaxy, seen from inside, looking across. We're not outside observers peering in. We're residents, looking at the ceiling of our cosmic room. Light itself, traveling faster than anything else in the universe, would need 100,000 years to cross from one edge of this room to the other. This realization changes everything about how we see our place in the cosmos. Earth isn't just our home. The solar system isn't just our neighborhood. The entire Milky Way becomes the larger structure we belong to. Beyond that, when you start thinking about galaxy clusters and superclusters, the sense of connection begins to fade. But the Milky Way, with its gravity binding together, stars and gas and dust, that's still something we can meaningfully call home. Our particular address in this vast galaxy sits on something called the Orion Spur, a relatively small arm branching off between two much larger spiral arms. Think of it as a quiet suburb, not too crowded with stellar neighbors, not too empty either. This location might be part of what makes life possible here. We're not constantly bombarded by radiation from too many nearby stars, but we're not so isolated that we lack the raw materials for new star formation. The Orion Spur represents our neighborhood on a galactic scale, and like any neighborhood, it has its own character, its own advantages and challenges. If you zoom in, home becomes the solar system. Zoom out, and home is this spiral arm. Zoom further out, and home encompasses the entire galactic disk. Each level of scale shifts what we mean by home, yet it all remains part of the same enormous structure. For most of human history, people had no idea they lived inside a galaxy at all. They saw the stars as lights fixed to a dome overhead, or perhaps scattered randomly across infinite space, without any particular pattern. Only in the early 20th century did astronomers prove that the Milky Way was actually a galaxy, and that countless other galaxies existed beyond it. Before that discovery, when people said universe, they meant what we now call a single galaxy. This shift in perspective happened remarkably recently, within the span of just a few generations. Before, home was everything there was. Now, home is one galaxy among billions. It shows how dramatically our sense of place can change as knowledge expands, how the boundaries of belonging can suddenly leap outward to encompass scales we never imagined. There's another layer to consider: the way dust and gas between stars creates a kind of cosmic fog, obscuring our view toward the galactic center. Much of our own galaxy remains hidden from us, as if we were trying to understand our hometown, while half the streets were covered in mist. Yet through radio waves, infrared surveys and careful observations of stellar motion, we've managed to map these hidden regions, to reconstruct the shape of our home from fragments and inferences. This process of piecing together the unseen has become part of what it means to belong to the Milky Way. Home isn't just what we can see directly, it's also the structures we deduce, the patterns we uncover through patient observation and clever techniques. Our galaxy home includes both the visible and the invisible, both the obvious and the mysterious. Consider the sheer number of stars sharing this space with us. Somewhere between 100 billion and 400 billion, depending on which estimates you trust. Each one potentially has planets. Some of those planets might harbor life. Our sun sits somewhere in the middle of this vast population, neither the largest star nor the smallest, neither at the galactic center nor at the edge. When we think of home on Earth, we usually imagine a specific location, a particular address, a sense of being rooted in one place. Galactic home feels different, more diffuse, less about individual location, and more about being part of a system where gravity ties everything together. To call the Milky Way home means accepting membership in this enormous community of stars, this collective identity that stretches across 100,000 light-years. The name itself, Milky Way, comes from that faint river of light, visible on clear, dark nights. Ancient observers saw it as milk spilled across the heavens, but different cultures interpreted this same streak of light in their own ways. Some saw a path for spirits, others a scar across the sky, still others the backbone of some cosmic creature. Each culture took the same phenomenon and wove it into their own story of place and meaning. Science later added measurements and structure to these ancient observations, but that fundamental feeling of being part of something vast and mysterious was already there in human consciousness. Home among the stars isn't just a scientific concept, it's also deeply cultural, built from the stories we tell to explain our connection to the cosmos. The numbers and distances matter, but so do the narratives that help us feel at home in such an enormous space. The question of where our galaxy ends becomes fascinating when you consider the scattered satellites that dance around its edges. Small companion galaxies like distant cousins follow orbital paths bound by the Milky Way's gravitational embrace. Some astronomers consider these wandering companions as genuine parts of our cosmic family. Others see them as neighboring entities, close but fundamentally separate. This disagreement reveals something profound about how we define boundaries in space. Nothing out there comes with clear borders, sharp lines, or definitive edges. The Milky Way functions as more than just a collection of stars. It operates as a protective shell around everything we know. Magnetic fields sweep through the galaxy, creating invisible barriers that deflect harmful radiation. Gas and dust distribute themselves in patterns that influence which cosmic rays reach our solar system. Even the mysterious dark matter, that invisible substance we can't directly observe, forms a halo that shapes our galactic environment. These forces work together, determining how often star systems might collide, how dense our stellar neighborhood remains, how stable conditions stay for planets like Earth. Our location within this vast structure isn't accidental. Scientists have proposed something called the galactic habitable zone, regions where conditions remain stable enough for complex life to develop. Move too close to the galactic center, and intense radiation would make survival nearly impossible. Venture too far toward the outer edges, and the heavy elements necessary for planet formation become incredibly scarce. We occupy a middle ground, a cosmic sweet spot, that mirrors the habitable zone around individual stars. This positioning suggests that our sense of home extends beyond Earth, beyond our solar system, into the very architecture of the galaxy itself. What makes this cosmic home even more intriguing is its constant motion. Our sun races around the galactic center at roughly 800 to 3,000 kilometers per hour. Despite this incredible speed, completing one full orbit takes about 225 million years. Human civilization hasn't existed long enough to witness even a single galactic rotation. The dinosaurs lived in a completely different sector of the Milky Way than we inhabit today. Every moment carries us along a vast circular journey, making home less about a fixed location and more about a shared voyage through space and time. This motion connects us to even larger cosmic structures. The Milky Way belongs to a collection called the Local Group, which includes the Andromeda Galaxy and dozens of smaller companions. Beyond that lies the Virgo supercluster, an enormous gathering of galaxy groups. Yet, as these structures grow in scale, they feel less personal, less like home. Distance dilutes our sense of connection. The galaxy remains the largest structure we can genuinely claim as our cosmic address, the furthest boundary where belonging still feels tangible and meaningful. Understanding our galaxy's shape helps explain why it feels so much like home. The Milky Way presents itself as a barred spiral, with a stretched central bar from which elegant arms curve outward. This bar alone spans tens of thousands of light years, making even seemingly minor features absolutely immense by human standards. The spiral pattern isn't fixed like a rigid pinwheel. Instead, these arms represent density waves, regions where stars and gas temporarily crowd together before continuing their journeys. This crowding triggers new star formation, giving the spiral arms their characteristic bright appearance. The central bulge contains the heart of our galaxy, a roughly spherical collection of mostly older stars surrounding a supermassive black hole. This black hole, known as Sagittarius A star, contains about 4 million times the mass of our Sun. The bulge spans thousands of light years, creating a dense stellar environment far more crowded than our local neighborhood. Stars there orbit much closer together, experiencing gravitational influences we can barely imagine from our relatively quiet corner of space. Most familiar galactic features reside within the thin disk, a flattened structure only about 1,000 light-years thick, but stretching roughly 100,000 light-years across. This disk contains the spiral arms, star-forming regions, vast gas clouds, and the majority of bright stars we observe. Our Sun follows an orbit within this disk, occasionally bobbing slightly above and below the central plane over millions of years. This thinness creates the luminous band we see stretching across Earth's night sky, the visual signature of our edge on view through the galactic plane. The galaxy extends far beyond its visible disk into something called the halo, a roughly spherical region containing scattered stars, ancient star clusters, and vast amounts of dark matter. This halo reaches hundreds of thousands of light-years outward, encompassing a volume much larger than the bright disk we typically picture. The halo remains incredibly sparse, with stars separated by enormous distances, yet it plays a crucial role in galactic dynamics. Globular clusters, ancient collections of stars, follow elongated orbits through this halo region, some swinging far from the galactic center before returning in cosmic cycles lasting hundreds of millions of years. This complex structure, with its disk, bulge, arms, and halo, creates an environment where patterns persist across vast scales of space and time. The interplay between visible matter, dark matter, magnetic fields, and gravitational forces generates a stability that has persisted for billions of years. Without this stability, the conditions necessary for planets, chemistry, and ultimately life might never have developed. Our cosmic home represents not just a location, but a delicate balance of forces that makes existence possible across scales from atoms to star systems. Ancient star clusters drift through the far reaches of space, marking territories we can barely imagine. These stellar groupings, some of the universe's oldest residents, wander through what astronomers call the galactic halo. They're like breadcrumbs, showing us just how enormous our galaxy really is. The bright center we might picture when we think of the Milky Way. That's just the beginning of the story. Stars move in ways that don't quite make sense, at least not if we only count what we can see. Out in the distant parts of our galaxy, stars should be crawling along slowly, barely held by gravity's weak grip. Instead, they're racing around at speeds that suggest something massive is out there, something we can't detect with our eyes or telescopes. This invisible presence, dark matter, wraps around our entire galaxy like a ghostly embrace. The whole thing spins, but not the way a dinner plate might spin on your finger. Different regions rotate at their own pace, creating this intricate dance of motion. Stars closer to the center zip around quickly, while those farther out take their time. But that dark matter changes everything, keeping outer stars moving faster than they should. It's one of the clearest hints we have that most of our cosmic neighborhood remains hidden from view. This invisible scaffolding extends far beyond anything we can photograph. The galaxy's true boundaries stretch into darkness, held together by matter that reveals itself only through its gravitational pull. Without this unseen framework, the beautiful spiral arms we associate with our galaxy might simply drift apart, like smoke dissolving in air. Motion and structure become the same thing when you're dealing with billions of stars. Each one follows its own path, but together, they create the patterns we recognize. It's a bit like watching a murmuration of starlings, where individual movement creates collective beauty. The galaxy's shape emerges from this cosmic choreography, where gravity conducts an orchestra of unimaginable size. Not every galaxy chooses the spiral path. Some are shaped like footballs, massive collections of stars with no distinct arms or patterns. Others look chaotic, twisted by encounters with neighboring galaxies. The Milky Way spiral structure represents just one solution to the puzzle of how matter organizes itself in space. Our galaxy sports what astronomers call a central bar, a elongated structure of stars that cuts through the middle. From this bar, spiral arms unfurl outward, creating the classic pattern we see in textbook illustrations. 4 main arms wind around the center, with smaller branches and spurs adding complexity to the design. Its architecture, on a scale that dwarfs human comprehension. The ancient clusters in the halo tell their own story of age and endurance. These stellar communities formed when the universe was young, when the first generation of stars was still learning how to shine. They've watched our galaxy take shape over billions of years, silent witnesses to cosmic evolution. Mapping this structure from our position inside proves remarkably challenging. Imagine trying to understand the layout of a vast city while standing on one street corner, surrounded by fog. Astronomers use radio waves to trace gas clouds, infrared light to peer through cosmic dust, and careful measurements of stellar positions to piece together the bigger picture. Space missions have revolutionized our understanding by tracking the movements of over 1 billion stars. These surveys reveal the galaxy's skeleton, showing how spiral arms emerge from the gravitational dance of matter and motion. It's detective work on a cosmic scale, where each new measurement adds another piece to an enormous puzzle. The shape we inhabit today won't last forever. Spiral arms may tighten or loosen over geological time. Interactions with smaller galaxies continue to stir the mix, adding new complications to an already complex system. In roughly 4 billion years, our entire galaxy will collide and merge with its neighbor Andromeda, creating something entirely new. This future collision will likely erase the spiral structure we know today, transforming both galaxies into a single elliptical system. The arms, the bar, the familiar patterns, all will be reshuffled into a different cosmic architecture. What we call home represents just one chapter in a much longer story of galactic evolution. Boundaries become fluid concepts when dealing with galactic structure. There's no sharp edge where the Milky Way stops and empty space begins. Instead, star density gradually decreases as you move outward, like the way a city transitions into suburbs and then countryside. Astronomers speak of characteristic distances rather than definite borders, acknowledging that our galaxy fades into intergalactic space rather than ending abruptly. The disk, where most familiar stars reside, has its own measurable limits. But the halo extends much farther, populated by those ancient clusters and dark matter. Beyond that, the galaxy's gravitational influence reaches even farther, creating a sphere of subtle effects that extends into the void between galaxies. Gravity orchestrates this entire cosmic symphony. Without its constant pull, the bar, arms, disk, and halo would simply drift apart, leaving behind only scattered stars in empty space. Instead, gravitational attraction maintains coherent structure across billions of years. Every star pulls on every other star, creating a delicate balance that preserves the galaxy's form. The central bulge, where older stars cluster in a dense spherical region, adds another layer to this gravitational architecture. These stars formed early in the galaxy's history, when star formation rates were much higher than today. They represent a different era of cosmic evolution, preserved in the galaxy's central regions. Our position in what astronomers call the Orion Spur gives us a particular perspective on all this structure. We're located between major spiral arms, in a relatively quiet region where star formation proceeds at a moderate pace. This galactic suburb provides a stable environment, protected from the more chaotic regions near the center or the sparse conditions at the galaxy's edge. The spiral arms themselves influence conditions throughout the disk. As they sweep through different regions, they compress gas clouds and trigger new episodes of star formation. These density waves move through the galaxy like ripples on a pond, creating the bright patterns we associate with spiral structure. Stars don't stay in the arms permanently. Instead, they drift in and out as they orbit the galactic center. Dark matter's invisible presence shapes everything from the largest scales down to local stellar neighborhoods. This mysterious substance outweighs all visible matter by roughly 5 to 1, making it the dominant gravitational influence in our cosmic region. Its distribution determines how fast stars orbit, how stable spiral arms remain, and how the galaxy responds to external perturbations. The galaxy's rotation curve, that relationship between distance and orbital speed, provides one of our clearest windows into dark matter's effects. In a solar system, planets farther from the Sun move more slowly, following predictable patterns based on the central mass. Galaxies behave differently, with outer regions moving faster than expected, revealing the presence of extended dark matter halos. Temperature and chemistry vary throughout the galactic disk, creating different environments for star formation and planetary systems. The inner regions, enriched by generations of stellar evolution, contain more heavy elements than the outer reaches. Our solar system formed in a region with just the right mixture of elements to support rocky planets and complex chemistry. The interstellar medium, that thin soup of gas and dust between stars, plays a crucial role in maintaining galactic structure. This material feeds ongoing star formation while carrying away energy from stellar explosions. Its distribution traces spiral arms and reveals how matter flows through the galaxy over cosmic time. Magnetic fields thread through this entire structure, though they remain largely invisible to casual observation. These fields influence how charged particles move through space, how stars form from collapsing gas clouds, and how energy from stellar explosions propagates through the galaxy. They add another layer of complexity to an already intricate system. From our small corner of this vast structure, we can barely perceive the whole, yet we remain intimately connected to every part of it. The Sun's steady orbit carries us around the galactic center once every 220 million years or so, a journey that defines our cosmic address. The spiral arms influence when and where new stars form in our neighborhood, affecting the long-term evolution of our stellar environment. Looking up at the night sky, we see scattered points of light, but there's so much more happening in the spaces between. Our galaxy, the Milky Way, stretches out in a vast spiral pattern that we can barely comprehend from our tiny vantage point on Earth. Those graceful, sweeping arms that define the galaxy's shape aren't what they appear to be at first glance. When we imagine spiral arms, we often think of them as solid, permanent structures, like the spokes of a wheel or ribbons frozen in space. But this couldn't be further from the truth. These arms are more like cosmic traffic jams, temporary gatherings where stars, gas, and dust pile up in higher concentrations. It's a bit like watching waves roll across the ocean. The wave moves forward, but the water itself mostly stays in place, rising and falling as the pattern passes through. This constant movement explains something profound about our galaxy. Stars don't stay locked in their arms forever. They drift in and out of these regions as they complete their long orbits around the galactic center. A star might spend millions of years inside an arm, then wander into the quieter spaces between arms, only to enter another arm much later in its life. Our own sun probably formed inside one of these busy spiral arms billions of years ago, before eventually settling into our current, more peaceful neighborhood. We live in what astronomers call the Orion Spur, which sounds grand, but is actually just a minor arm, a cosmic side street, wedged between two much larger structures. On one side of us lies the Sagittarius arm, on the other, the Perseus arm. From our position, it's remarkably difficult to map the full spiral pattern. Imagine trying to understand the layout of a vast city while standing in the middle of it. That's essentially what we're doing when we study our galaxy's structure. Astronomers have found clever ways around this problem. They use radio telescopes to peer through the dust that blocks our view of distant stars. Radio waves can travel through cosmic dust clouds that would completely hide visible light. By tracking hydrogen gas and molecular clouds, with these radio observations, scientists have slowly built up a map of the galaxy's spiral structure. What they've discovered is that the Milky Way has 4 main arms, with various smaller spurs and branches connecting them, creating a complex web of stellar highways. The arms shine brightly because they're stellar nurseries, places where new stars are constantly being born. When gas clouds drift into these higher density regions, they get squeezed and compressed. This compression is often enough to trigger the collapse of massive molecular clouds, causing them to fragment and form new stars. The process is surprisingly violent and chaotic, with stellar winds and radiation from newly formed stars, sculpting the surrounding gas into beautiful, complex shapes. Young, massive stars burn incredibly hot and shine with brilliant blue light. They're like cosmic light bulbs, illuminating the spiral arms and making them visible across vast distances. But these stellar giants live fast and die young, burning through their nuclear fuel in just a few million years. They never have time to wander far from their birthplace, so they essentially outline the spiral arms for us, creating a glowing map of the galaxy's structure. Without these short-lived, massive stars, the spiral arms would be nearly invisible. The arms would still exist as regions of higher density, but we wouldn't be able to see them shining across space. It's one of those beautiful cosmic coincidences. The very process that creates the arms also provides the light that reveals them to us. Inside these stellar nurseries, the cycle of creation and destruction plays out on an enormous scale. Stars form in clusters, sometimes hundreds or thousands at a time. The most massive stars explode as supernovas after just a few million years, scattering heavy elements like carbon, oxygen, and iron into the surrounding space. These elements, forged in the hearts of dying stars, eventually become part of the next generation of stars and planets. This constant recycling means that the spiral arms are like cosmic factories, continually renewing and enriching the galaxy. Each generation of stars is slightly richer in heavy elements than the last. Planets like Earth, made primarily of rock and metal, could only form after many generations of stars had lived and died, building up the supply of heavy elements in the galaxy. The persistence of spiral structure over billions of years puzzled astronomers for decades. If the arms were simply groups of stars moving together, they should have wound up tighter and tighter as the galaxy rotated, eventually disappearing entirely. The solution came from something called density wave theory. In this model, the spiral arms aren't fixed groups of stars, but rather waves of density that sweep around the galaxy. Think of it like a traffic jam on a highway. The jam itself maintains its position, even though individual cars are constantly entering and leaving it. Similarly, spiral arms persist as waves of compression moving through the galaxy, while individual stars and gas clouds pass in and out of them. This elegant solution explains how galaxies can maintain their spiral structure for billions of years without winding themselves into tight knots. But the story isn't quite that simple. Astronomers have discovered that different galaxies display a wide variety of spiral patterns. Some have two perfectly symmetric arms, others have multiple arms that break apart and reconnect. Some spiral patterns seem to come and go, forming and dissolving over hundreds of millions of years. The Milky Way appears to fall somewhere in the middle of this spectrum, with a complex mix of major arms and smaller spurs. Our galaxy also has a central bar, an elongated structure of stars that helps drive the spiral pattern. This bar rotates more slowly than the outer disk, creating the conditions that maintain the spiral waves. It's like a cosmic stirring spoon, constantly mixing the galaxy and keeping the spiral structure alive. From our perspective inside the galaxy, the spiral arms define much of what we see in the night sky. Many familiar constellations contain stars that belong to our local arm, the Orion Spur. The famous Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion, is actually a massive star-forming region within our spur. Other bright nebulae and star clusters trace the outlines of nearby arms, creating the patterns we've learned to recognize. When we look toward the center of the galaxy, our view is largely blocked by dust clouds. But in other directions, we can see the concentrations of young, bright stars that mark the locations of spiral arms. These stellar landmarks have guided astronomers in mapping the galaxy's structure, one bright star cluster at a time. The chemical evolution of the galaxy is intimately tied to the spiral structure. Because star formation is concentrated in the arms, these regions become enriched with heavy elements more quickly than the spaces between arms. As stars age and move out of the arms, they carry these elements with them, gradually spreading the chemical enrichment throughout the galaxy. This process has profound implications for the formation of planets and the possibility of life. Rocky planets like Earth, require significant amounts of heavy elements which were rare in the early universe. The concentration of star formation in spiral arms helped build up the supply of these elements relatively quickly, making Earth-like planets possible much sooner than they would have been in a galaxy without spiral structure. The arms are also shaped by the galaxy's interactions with its smaller neighbors. Over billions of years, the Milky Way has absorbed dozens of dwarf galaxies, and these cosmic meals have stirred the galactic disk, enhancing spiral patterns and creating new structures. Streams of stars torn from these smaller galaxies weave through the disk, adding complexity to the spiral arms. The Sagittarius dwarf galaxy is currently being shredded by the Milky Way's gravity, leaving behind streams of stars that influence the outer regions of our galaxy. These interactions show us that spiral arms aren't isolated features, they're part of a larger cosmic ecosystem, where galaxies grow and evolve through mergers and interactions. When astronomers search for planets around other stars, they often focus their attention on the spiral arms. Young star systems are more common there, and young stars are often the best targets for planet hunting missions. Many of the thousands of exoplanets discovered in recent years orbit stars located within or near spiral arms. When we wonder about the possibility of life elsewhere in the galaxy, we're really wondering about life that might exist in these same swirling structures. It's worth remembering that our perspective shapes everything we know about spiral arms. From our position in the Orion Spur, this minor arm seems like our entire cosmic neighborhood. But to hypothetical astronomers living near a star in the Perseus arm, our spur might seem like an insignificant bump in the galactic structure. This relativity of scale reminds us that these immense cosmic structures are also intimately personal. They define the local environment, where we, and perhaps other civilizations, call home. Mapping the spiral arms remains one of astronomy's ongoing challenges. We can't step outside the galaxy to see its structure from above, so we have to rely on careful, indirect methods. Astronomers measure the distances to young, bright stars using parallax, then plot their positions to trace the arms. They map the distribution of giant molecular clouds, the raw material from which stars form. They track the motions of gas clouds, using radio telescopes, building up a three-dimensional picture of the galaxy's structure. The European Space Agency's Gaia mission has revolutionized this effort by measuring the precise positions and motions of over 1 billion stars. This vast dataset has allowed astronomers to see patterns in stellar motion that confirm many theoretical predictions about spiral structure while revealing new details about the galaxy's complexity. What emerges from all this painstaking work is a picture of spiral arms as dynamic. Living features of our galaxy, they're not permanent architectural elements, but they're long-lived enough to define the Milky Way's appearance for hundreds of millions of years at a time. They represent both a physical process, the concentration of matter into waves of density, and a visual phenomenon, the most recognizable feature of our galactic home. In contemplating these vast spiral structures, we're confronted with our own place in an incomprehensibly large and dynamic system. The spiral arms connect us to the largest scales of cosmic organization while simultaneously defining our local cosmic environment. They remind us that we're part of something much larger than ourselves, participants in a grand cosmic dance that has been unfolding for billions of years and will continue long after our sun has faded away. When darkness falls and you crane your neck upward, maybe a few thousand pinpricks of light reveal themselves to your eyes. It feels like plenty. But here's the thing, what you're seeing barely scratches the surface. The Milky Way, our cosmic neighborhood, holds somewhere between 100 billion and 400 billion stars. That's billion with a B. Think about that for a moment. Every single point of light you've ever noticed on a clear night, every constellation you've memorized, every shooting star you've wished upon, all of it combined represents less than 1% of what's actually out there. The rest remains hidden, not because it's impossibly far away, but because it's simply too dim for our eyes to detect. This enormous range in estimates, from 100 billion to 400 billion, tells us something profound about the challenge astronomers face. Counting stars isn't like counting pebbles on a beach. Stars come in wildly different sizes and brightnesses. Some are massive blue giants, burning so intensely they can be spotted from incredible distances. Others are tiny red dwarfs, so faint they practically whisper their existence into the void. The majority of stars, roughly 3/4 of them, fall into this second category. They're the cosmic equivalent of nightlights, glowing just enough to keep burning for trillions of years, while our sun will eventually expand and die in about 5 billion years. These little red dwarfs will keep shining long after every other star has burned out. They're the ultimate survivors of the galaxy, yet we can barely see them from our solar system. Here's where it gets interesting. We're trying to count all these stars while sitting inside the very galaxy we're studying. Imagine being dropped in the middle of a dense forest and asked to count every tree. You can see the ones nearby pretty clearly, but the distant ones blur together. Branches and leaves block your view in certain directions. Some trees hide behind others. That's exactly the predicament astronomers find themselves in. Clouds of dust and gas drift between us and distant stars, obscuring entire regions of the galaxy. What looks like empty space might actually be teeming with stars we simply can't detect. So scientists have developed clever workarounds, studying small patches of the sky in incredible detail, then extrapolating those findings across the entire galactic structure. The Gaia spacecraft has been particularly helpful in this cosmic census. It's mapped over 1 billion stars, recording not just their positions, but also how they're moving through space. Even so, that billion represents only a tiny fraction of the galaxy's total population. It's like studying a single neighborhood and using that data to understand an entire continent. But here's something that complicates the count even further. Many stars don't live alone. They form pairs, triplets, even larger groups, all orbiting around each other in cosmic dances that can last billions of years. From our perspective, these multiple star systems often look like single points of light. If you assume every twinkle represents just one star, you'll dramatically underestimate the true population. Binary stars, as they're called, might actually be more common than solitary stars, like our sun. This means that when we peer into space and count individual light sources, we might be missing half the story. Each dot of light could represent 2 stars, 3 stars, sometimes even more, all locked in gravitational embrace. The galaxy itself has structure, like a vast city with different neighborhoods. Most stars cluster in the thin disk, where spiral arms sweep through space like frozen whirlwinds. This is where new stars are still being born, where giant molecular clouds collapse under their own weight to ignite nuclear fusion. The disk is crowded, bustling with stellar activity. At the galaxy's heart sits the bulge, a dense concentration of older stars. These are the cosmic elders, formed when the galaxy was young and chaotic. They're packed together much more tightly than the stars in our local neighborhood, creating a brilliant glow at the galactic center. Beyond that lies the halo, a sparse sphere of ancient star clusters orbiting the galaxy's edge like distant satellites. Each region requires its own counting strategy. You can't just measure the star density in one area and multiply by the galaxy's total volume. The disk, bulge, and halo each have their own characteristics, their own types of stars, their own histories written in light. Consider the scale of these numbers for a moment. If you decided to count stars one by one, saying each number aloud at a rate of 1 per second, never stopping to eat or sleep, it would take you thousands of years to finish. That's assuming the lower estimate of 100 billion. If the true number approaches 400 billion, you'd need several additional millennia. The human brain simply isn't equipped to grasp quantities this vast. We need analogies to make sense of them. There are roughly 8 billion people on Earth right now. If you wanted to give each person their own personal collection of stars, you could assign more than a dozen stars to every human being and still have billions left unclaimed. This abundance challenges our intuitions about rarity and uniqueness. We often think of stars as special, extraordinary objects, and they are, in the sense that each one is a nuclear furnace capable of burning for millions or billions of years. But they're also surprisingly common, scattered through space like grains of sand on an endless beach. The distribution of stellar types reveals something beautiful about cosmic diversity. Those tiny red dwarfs that make up the majority will outlive everything else. They're the tortoises in this cosmic race, burning their fuel so slowly and efficiently that they could theoretically shine until the universe itself grows cold and dark. Meanwhile, the massive blue giants burn bright and fast, living only millions of years before exploding as supernovas. These stellar explosions aren't just dramatic endings, they're essential beginnings. When massive stars die, they scatter heavy elements throughout the galaxy. Carbon, oxygen, iron, all the elements that make planets and life possible were forged in stellar cores and distributed by these cosmic detonations. Every atom in your body, except for hydrogen, was once part of a star that lived, died, and gave its substance to the universe. Star clusters add yet another layer to this cosmic complexity. Open clusters are stellar nurseries, places where dozens or hundreds of stars are born together from the same cloud of gas and dust. Over time, these stellar siblings drift apart, but for millions of years, they travel through space together like a cosmic convoy. Globular clusters are different beasts entirely. These are ancient, tightly bound collections of hundreds of thousands of stars, some of the oldest objects in the galaxy. They orbit in the halo, like cosmic time capsules, preserving information about conditions that existed over 10 billion years ago. Including these clusters in our star count adds not just numbers, but also deep history. Then there's the question of stellar remnants. When stars die, they don't simply disappear. Smaller stars like our Sun will eventually become white dwarfs, incredibly dense objects about the size of Earth, but containing most of the original star's mass. Larger stars might become neutron stars, objects so dense that a teaspoon would weigh as much as a mountain. The most massive become black holes, regions of spacetime where gravity has become so strong that nothing, not even light, can escape. These objects are no longer shining in the conventional sense, but they're still part of the galaxy's population. White dwarfs, in particular, are numerous and represent the final fate of most stars. They're incredibly long-lived, slowly cooling over trillions of years. In the far future, when star formation has ceased and the last red dwarfs have finally burned out, white dwarfs might be the only remnants of our galaxy's stellar era. The sheer number of stars also multiplies the possibilities for planets, and by extension, life. Recent surveys suggest that planets are common, perhaps more common than stars themselves, since many stellar systems host multiple worlds. If even a tiny fraction of stars have planets in the right location to support liquid water, the Milky Way could contain tens of billions of potentially habitable worlds. This transforms our star count from an abstract number into something much more profound. Each star represents not just a ball of hot gas, but a possible solar system. Each solar system might host rocky planets, gas giants, moons, and maybe even life. The number of stars becomes a measure of cosmic possibility, of places where chemistry might have evolved into biology, where other forms of consciousness might be asking the same questions about their place in the universe. The age distribution of stars tells the galaxy's story. Young, hot stars concentrate in the spiral arms, marking regions where star formation is currently active. Older stars dominate the bulge and halo, showing us where the galaxy's earliest stellar generations took hold. By studying different stellar populations, astronomers can reconstruct billions of years of galactic history. The oldest stars are particularly interesting because they formed when the universe contained almost no heavy elements. These ancient suns are made almost entirely of hydrogen and helium, the primordial elements created in the Big Bang. They're like archaeological artifacts, preserving information about cosmic conditions that existed when the universe was young and the first galaxies were just beginning to form. Despite all our advances in astronomy, the exact number of stars remains uncertain. That uncertainty isn't a failure of science. It's a reminder of the galaxy's immensity. Whether the true count is closer to 100 billion or 400 billion hardly matters when either number exceeds our ability to truly comprehend it. What matters more is the recognition that we exist within something unimaginably vast and rich. Every time you look up at the night sky, you're seeing the tiniest sample of a collection so large it defies intuition. The invisible stars outnumber the visible ones by millions to one. The galaxy extends far beyond what our eyes can detect, fading gradually into the emptiness between galaxies, rather than ending at some distinct boundary. In trying to count the uncountable, we're really trying to understand our context, to measure the stage on which the cosmic drama unfolds. The numbers themselves are less important than what they represent. A universe filled with light, energy, and possibility on a scale that makes every star, including our own sun, seem simultaneously precious and abundant. The galaxy is not just our home, it's a vast ecosystem of stars in different stages of life, death, and rebirth. Some are being born right now, in stellar nurseries hidden behind veils of dust and gas. Others are in their prime, steadily converting hydrogen to helium in their cores. Still others are approaching the end, swelling into red giants, or preparing for the violent collapse that will mark their final moments. This ongoing cycle of stellar birth and death has been continuing for billions of years, and will continuing for billions more. Each generation of stars enriches the galaxy with heavier elements, making possible the formation of planets, and eventually, life itself. We are not separate from this process. We are part of it, made from the ashes of ancient stars, and destined to return our atoms to space when our own star reaches the end of its life. Looking up at the night sky, you might think you're seeing the galaxy in all its glory. The truth is, you're only catching glimpses through a cosmic curtain. Most of the Milky Way remains completely hidden from our eyes, veiled behind countless tiny particles drifting through space. These aren't the dust bunnies you'd find under your bed. Interstellar dust consists of microscopic grains made from carbon, silicon, and frozen gases. They're scattered across distances so vast that even though each grain is smaller than the width of a human hair, together they form an enormous barrier between us and the stars. Think about how a single sheet of tissue paper barely blocks any light, but stack thousands of them together, and suddenly you can't see through at all. That's essentially what's happening on a galactic scale. These dust particles clump into clouds and long, thread, like structures that stretch for hundreds of light years. The dust doesn't just block light, it plays favorites with different colors. Blue light gets scattered and absorbed much more easily than red light. This means stars shining through dusty regions appear redder than they actually are. It's similar to how the sun looks redder at sunset, when its light has to travel through more of Earth's atmosphere. For astronomers trying to measure how far away stars are, this color shifting creates real headaches. Imagine trying to judge the distance to a streetlight at night, but someone keeps changing the color of the bulb. You'd constantly second guess whether it looks dim because it's far away, or because something is filtering the light. Near the center of our galaxy, the dust becomes so thick that visible light simply cannot penetrate. For centuries, the heart of the Milky Way remained completely invisible to us. We knew something massive had to be there, holding all those stars in orbit, but we couldn't see what. Only when we learned to look with different types of light, like infrared and radio waves, could we finally peer through this cosmic fog. What we discovered was extraordinary: a dense bulge of ancient stars, and at the very center, a supermassive black hole containing millions of times more mass than our sun. The famous dark streak you can see cutting across the Milky Way on clear summer nights isn't empty space. It's actually the Great Rift, a series of dense dust clouds blocking the light from stars behind them. These dark lanes have captured human imagination for thousands of years. Different cultures saw them as cosmic rivers, or the pathway spirits took to reach the afterlife. But here's where things get philosophically interesting. These same dust clouds that hide stars from us are actually stellar nurseries. Inside their cold, dark depths, gravity slowly pulls material together. Eventually, these clumps become dense enough to ignite nuclear fusion, and new stars are born. The Orion Nebula, visible even with small telescopes, shows this process happening right now. What looks like a glowing cloud is actually a massive stellar maternity ward, where dozens of new stars are taking their first breaths. The dust that seems to obstruct our view is simultaneously creating the next generation of suns. This presents us with an interesting paradox. The very thing that limits our vision is also the raw material for everything we know. Those microscopic dust grains eventually stick together, forming pebbles, then rocks, then asteroids, and finally planets. Without cosmic dust, there would be no Earth, no oceans, no mountains, and certainly no life. The distribution of dust throughout the galaxy is far from uniform. It's more like Swiss cheese, with thick regions and clear corridors, scattered seemingly at random. This patchwork means our view of the cosmos changes dramatically, depending on which direction we look. Toward some parts of the sky, we can see stars thousands of light years away, with crystal clarity. In other directions, dust blocks our view after just a few hundred light years. It's like trying to navigate a city where fog randomly appears and disappears on different streets. To work around this cosmic hide-and-seek, astronomers have become incredibly creative. Radio waves pass through dust almost as if it weren't there. By tuning into specific radio frequencies, we can detect hydrogen gas floating between the stars, mapping the galaxy's spiral arms, even where dust makes them invisible to our eyes. Infrared light also penetrates dust much better than the visible light our eyes detect. Space telescopes equipped with infrared detectors have revealed millions of stars near the galactic center that had never been seen before. It's like suddenly being given night vision goggles in a dark room. X-rays and gamma rays, at the opposite end of the spectrum, also bypass dust completely. Though instead of showing us ordinary stars, these high-energy wavelengths reveal more violent cosmic events, exploding stars, matter falling into black holes, and other energetic processes that heat gas to millions of degrees. By combining observations from all these different types of light, astronomers can build a more complete picture of our galaxy. It's like having multiple witnesses to the same event, each seeing different details that help piece together the full story. Even with all these tools, dust continues to complicate our understanding. Distance measurements remain uncertain because we can never be completely sure how much dust lies between us and any particular star. New surveys constantly refine our maps of the Milky Way, but each discovery seems to reveal new complexities rather than simplifying the picture. The sheer amount of dust in our galaxy is staggering. Although it makes up only about 1% of all the material floating between stars, that still adds up to millions of times the mass of our Sun. Most of this dust concentrates in a thin layer along the galactic plane, which explains why the Milky Way appears as a band across our sky rather than a uniform glow. Above and below this dusty disk, our view clears dramatically. We can see distant galaxies billions of light years away, their light having traveled across most of the observable universe to reach us. It's ironic that we can sometimes see farther into space by looking away from our own galaxy's center. The dust has shaped not just what we see, but how we've learned to see. Many of the most important advances in astronomy came from attempts to peer through this cosmic veil. Infrared detectors, radio telescopes, and space-based observatories all developed partly from our frustration with dust's obstruction. Perhaps there's something poetic about our situation. We live inside this magnificent spiral galaxy, that we experience it as fragments and glimpses, rather than a grand vista. The beautiful spiral galaxy photographs in astronomy textbooks show what the Milky Way would look like if we could somehow step outside and view it face-on. Instead, we're like visitors in a vast cathedral, but one where fog drifts through the nave, sometimes revealing soaring columns and stained glass windows, sometimes hiding them completely. Our understanding comes not from a single moment of revelation, but from patiently collecting scattered impressions over time. The dust grains that limit our view today will eventually become part of new solar systems. Some might even contribute to planets where future life forms will evolve and perhaps develop their own astronomy. Those distant observers will face the same challenges we do, learning to see around the obstacles their universe presents. In a way, cosmic dust serves as a reminder of our place in the larger story. We're not outside observers looking in at the universe. We're participants, made from the same materials that both reveal and conceal the cosmos around us. The calcium in our bones, the iron in our blood, the carbon in our DNA, all were once part of those microscopic grains drifting between the stars. Every time we look up at the night sky, we're seeing a partial view shaped by this ancient dust. The dark lanes cutting across the Milky Way aren't empty spaces, but birthplaces of future worlds. The dimmed light of distant stars carries information not just about those suns, but about everything their light encountered on its journey to our eyes. Perhaps our limited view makes the universe more mysterious and beautiful than it would be if we could see everything clearly. The hidden depths remind us that reality extends far beyond what's immediately visible, and that understanding requires both patience and creativity. Distance becomes the invisible thread that weaves together our understanding of the cosmos. When you look up at the night sky, you're seeing a flat tapestry of lights, but behind that simplicity lies one of astronomy's greatest puzzles. Every point of light sits at a different distance, some close enough to touch in cosmic terms, others so remote they challenge our ability to measure at all. The challenge starts with something surprisingly familiar. Your brain performs distance calculations every moment of your waking life, using the slight difference between what your left and right eyes see. This biological trick, refined over millions of years of evolution, becomes the foundation for measuring the galaxy itself. Astronomers simply scaled up the concept, using Earth's entire orbit as their baseline instead of the few centimeters between your eyes. As our planet swings around the Sun, covering nearly 300 million kilometers in its yearly journey, nearby stars appear to shift against the more distant background. It's a tiny movement, barely detectable, even with our most sophisticated instruments. Imagine trying to measure the width of a small coin from thousands of kilometers away, and you begin to appreciate the precision required. The angles involved are measured in fractions of arcseconds, units so small they test the limits of what we can observe. This method, called parallax, works beautifully for stars within a few thousand light-years of Earth. But the galaxy stretches far beyond that comfortable bubble of measurement. For centuries, this limitation kept astronomers trapped in a relatively small neighborhood of space, unable to chart the true extent of their cosmic home. The breakthrough came with space telescopes, freed from the blurring effects of Earth's atmosphere. One particular space observatory mapped the positions and distances of over 1 billion stars, creating the most detailed, three-dimensional chart of the Milky Way ever assembled. This census revealed spiral arms we hadn't seen clearly before, measured the thickness of our galactic disk with new precision, and traced the faint halo of stars that surrounds everything else. Yet even with such remarkable achievements, parallax eventually fails us. The most distant stars refuse to shift enough for reliable measurement. Astronomers found their solution in the stars themselves. Some stars behave like cosmic lighthouses, pulsing with predictable brightness. These pulsating giants follow a remarkable rule. Their period of variation directly linked to their intrinsic luminosity. A star that pulses every few days will always be brighter than one that pulses every few hours. This relationship becomes a cosmic measuring stick, allowing astronomers to calculate distance by comparing a star's apparent brightness with its known true brightness. These pulsating variables can be seen across vast stretches of the galaxy, even in neighboring galaxies millions of light-years away. They've become essential markers for mapping the cosmos, bright enough to stand out against the background glow of countless fainter stars. Different types serve different purposes, some better for nearby regions, others for the most distant boundaries of our galactic neighborhood. Globular clusters, those ancient spherical collections of hundreds of thousands of stars, contain their own distance indicators. These stellar cities orbit far beyond the visible disk of the Milky Way, some more than 100,000 light-years from the galactic center. By measuring their distances accurately, astronomers discovered that our galaxy extends much farther than the spiral arms suggest. The clusters revealed a vast halo of dark matter and sparse stars, stretching hundreds of thousands of light-years in every direction. Red giant stars provide another measuring tool. When stars of certain masses reach a specific stage in their evolution, they achieve remarkably similar brightness levels. This consistency makes them useful standard candles, especially for intermediate distances where other methods become unreliable. White dwarf stars, the dense remnants left behind when smaller stars exhaust their fuel, also serve as distance markers under the right circumstances. Even stellar explosions contribute to the distance ladder. When a white dwarf star in a binary system accumulates enough material from its companion, it can trigger a runaway fusion reaction. These explosions, visible across millions of light years, reach nearly identical peak brightness. While they're more commonly used for measuring distances to other galaxies, they help calibrate the entire system of cosmic distance measurement. The challenge extends beyond simple measurement. Every distance estimate carries uncertainty, and those uncertainties accumulate as astronomers reach farther into space. If distances are underestimated, the galaxy appears smaller, denser, and younger than it really is. Overestimate them, and suddenly the Milky Way looks larger, more diffuse, and older. Entire theories about galactic structure depend on getting these measurements right. Dust complicates everything. The same particles that create beautiful nebulae and hide parts of the galaxy from view also affect how bright stars appear. Dust absorbs and redirects light, making distant stars look dimmer than they should. Without proper corrections, astronomers might think a star is much farther away than it actually is. They work around this by observing at infrared and radio wavelengths, which penetrate dust more easily, but corrections remain necessary. Stars don't stay still in their cosmic dance. They orbit the galactic center, following paths that take millions of years to complete. By measuring how stars move across the sky over time, and combining this with observations of their motion toward or away from us, astronomers can trace these orbital paths. The resulting picture reveals how mass is distributed throughout the galaxy, which in turn helps estimate its total size and extent. Statistical methods add another layer to the measurement toolkit. When individual stars can't be resolved clearly, astronomers can still estimate distances by studying the combined light of stellar clusters and comparing it to theoretical models. These techniques are less precise for single objects, but they help build the larger framework needed to understand galactic structure. The distance problem has shaped entire eras of astronomical discovery. Before accurate distance measurements became available, astronomers debated whether the Milky Way represented the entire universe. The realization that certain fuzzy nebulae were actually other galaxies millions of light years away depended entirely on distance calculations. Once the true remoteness of the Andromeda Galaxy became clear, it revolutionized our understanding of our place in the cosmos. Distance measurements determine where we draw the boundaries of our galaxy. If estimates are too conservative, the Milky Way's edge appears closer than it really is. If they're too generous, background galaxies might be mistakenly counted as distant members of our own stellar system. The precision of distance measurement directly affects the clarity with which we can define galactic boundaries. Stellar streams tell part of this story. These are the scattered remains of smaller galaxies that wandered too close to the Milky Way and were torn apart by its gravity. The resulting trails of stars stretch across hundreds of thousands of light years, marking paths through space that reveal the galaxy's gravitational influence. Following these streams requires accurate distance measurements at every step. The search for galactic edges becomes a journey through layers of cosmic archaeology. Each measurement technique extends our reach a little farther, like adding another ring of light around a campfire. Parallax illuminates the immediate neighborhood. Standard candles reach into the spiral arms, and statistical methods probe the outermost boundaries, where individual stars become too faint to study in detail. What emerges from this careful measurement is a galaxy far more extensive than early astronomers imagined. The bright spiral disk that dominates photographs represents only a fraction of the Milky Way's true extent. Surrounding everything lies a vast halo of dark matter, ancient stars, and globular clusters, extending the galaxy's influence across hundreds of thousands of light-years of space. This extended structure raises profound questions about where one galaxy ends and intergalactic space begins. The boundary becomes increasingly arbitrary as astronomers discover ever more distant objects still bound to our galactic system. Perhaps the question of edges says more about human psychology than cosmic reality, our need to categorize and define boundaries in a universe that may be fundamentally continuous. The heart of our galaxy tells a story that's both ancient and surprisingly active. Picture a vast collection of stars, roughly spherical in shape, swelling outward from the very center of the Milky Way. This is what astronomers call the bulge, and it's nothing like the quiet neighborhood where our solar system resides. These central regions are crowded beyond imagination. Stars packed together so densely that if you could somehow stand there, the night sky would blaze with brilliant light. Some of these stellar neighbors sit just a fraction of a light year apart, practically touching by cosmic standards. The whole region pulses with an energy that reaches across tens of thousands of light years, shaping how our entire galaxy behaves. Time moves differently in the bulge, or at least, time has left different marks there. Many stars burning in this central region are more than 10 billion years old. They formed when the universe itself was still young, when our galaxy was just beginning to take shape. Their advanced age shows in their color, a deeper red than the bright blue giants we see in the spiral arms. These ancient suns are cooler now, their nuclear fires burning more slowly after eons of steady fusion. But here's where things get interesting. Mixed among these elderly stars are much younger ones, cosmic teenagers that formed relatively recently. This creates a puzzle that astronomers are still trying to solve. How did new stars form in a region dominated by such old ones? The answer seems to lie in the flow of gas, funneled inward along invisible highways created by the galaxy's central bar structure. The bulge itself isn't perfectly round, which came as a surprise to many researchers. Instead, it has a boxy, almost peanut-like shape when viewed from the right angle. This odd geometry comes from the complex dance of stellar orbits, all influenced by the rotating bar that cuts through the galaxy's center. Stars don't just move in simple circles here, they puff up and down, creating this thickened, elongated structure. At the very heart of all this activity sits something we cannot see directly, yet its presence shapes everything around it. Sagittarius A star, a supermassive black hole, anchors the center of our galaxy with a mass 4 million times greater than our Sun. We know it's there because of the stars that orbit it, whipping around an invisible point at tremendous speeds. Their curved paths reveal the presence of something compact and incredibly massive. The environment near this black hole defies imagination. Gas clouds spiral inward, heating to millions of degrees as they approach the point of no return. Magnetic fields twist and tangle in ways that would make a pretzel jealous. Occasionally, material falling into the black hole produces sudden flares of radiation, brief reminders that the galactic center is anything but quiet. Studying this region presents enormous challenges. Thick clouds of dust block our view when we try to look with visible light. It's like trying to peer through fog, so dense that even the brightest stars become invisible. That's why astronomers have learned to see with different eyes, using infrared and radio telescopes that can pierce through the cosmic haze. These specialized instruments have revealed something profound about the bulge's role in galactic life. It's not just a collection of old stars sitting at the center, it's more like the foundation of a vast building. The mass concentrated in the bulge affects how stars move throughout the entire disk, influences the spiral arms, and even shapes the galaxy's overall rotation. Think of it as an anchor point, holding together forces that span hundreds of thousands of light years. Without this central mass, the inner regions of our galaxy would behave completely differently. The spiral arms might not maintain their elegant curves, the bar might not channel gas as efficiently, and the delicate balance that keeps everything in motion could collapse. The stars in the bulge also serve as a kind of fossil record, carrying chemical signatures that tell the story of how our galaxy evolved. Some are metal-poor, meaning they formed before generations of stellar death and birth had enriched space with heavy elements. Others contain more metals, evidence of later waves of star formation, when the interstellar medium had become richer in complex atoms. This chemical archaeology suggests that the bulge formed through a complex process, not all at once, but through multiple episodes, spread across billions of years. Some stars may have formed quickly in the galaxy's earliest days, while others came later through the gradual inflow of gas or mergers with smaller galaxies that wandered too close. From our position 26,000 light-years away, the bulge dominates the night sky when we look toward the constellation Sagittarius. That rich region crowded with stars and glowing nebulae is our window into the galactic center. What appears as a hazy glow to naked eyes is actually the combined light of billions of distant suns, packed together in unimaginable density. The bulge connects to everything around it in ways that create feedback loops affecting the entire galaxy. The central bar extends through it, the disk spreads outward from its edges, and the invisible halo surrounds it on all sides. This isn't an isolated structure, it's the central knot from which other components flow, tying the galaxy together through gravity and motion. Even though it seems impossibly remote, the bulge's influence reaches us directly. The gravity of this central mass shapes the orbit of our Sun and every other star in the disk. The stability we experience, the thickness of the galactic plane we inhabit, even the overall rotation that carries us around the galaxy, all depend on the bulge's massive presence. Looking at this central region also raises fascinating questions about boundaries. Where exactly does the bulge end and the disk begin? The transition is gradual rather than sharp, stellar density decreasing smoothly, outward, chemical compositions blending together, orbital patterns shifting by degrees rather than suddenly changing. This lack of clear edges reflects something deeper about how galaxies work, how structure emerges not from rigid boundaries, but from gradual transitions. For astronomers, the bulge serves as a humbling reminder of observation's limits. Even with the most advanced instruments, dust and distance make detailed study challenging. Each new survey adds information, but also reveals additional complexity. The more closely we look, the less simple the picture becomes. The bulge refuses to be reduced to neat descriptions, remaining both ancient and active, structured and diffuse, an archive of galactic history and a living system still evolving. Beyond the bright bulge, beyond even the spiral arms that define our galaxy's most recognizable features, lies something much larger and more mysterious. The galactic halo stretches far into space, a vast sphere of faint matter that envelops everything we normally think of as the Milky Way. It's largely invisible to casual observation, yet it may contain more mass than all the bright stars combined. Around our entire galaxy, there's this enormous sphere of incredibly old stars, just floating out there in the darkness. These ancient stellar wanderers move in completely random directions, nothing like the neat, organized rotation we see in the galaxy's main disk. They're the survivors of cosmic catastrophes that happened billions of years ago, when smaller galaxies got too close to our Milky Way and were completely ripped apart by gravity. Think about it, these stars we call halo stars, they're basically homeless now. They once belonged to their own little galaxies, had their own communities, their own stellar neighborhoods. But then our massive Milky Way came along, like some cosmic bully, and tore their homes to pieces. Now, they're scattered across unimaginably huge volumes of space, traveling on these stretched-out orbits that take them incredibly far from the galactic center. What's fascinating is that these stars are living fossils. They carry the memory of galactic evolution, written right into their very existence. Every one of them tells a story about collisions, mergers, and the violent history of how our galaxy grew up. It's like having witnesses to ancient crimes, except the crimes happened over billions of years, and the witnesses are balls of nuclear fire. The most spectacular residents of this stellar halo are these things called globular clusters. Each one is basically a tight ball containing hundreds of thousands of stars, all bound together by gravity. From our perspective on Earth, they look like fuzzy, glittering ornaments hanging in space through our telescopes. But really, they're more like cosmic lighthouses, marking the outer boundaries of our galactic territory. Some of these globular clusters orbit at distances greater than 100,000 light-years from the galactic center. That's an almost incomprehensible distance, yet they're still gravitationally bound to our galaxy. They swing out into the cosmic wilderness and then come swooping back, following these enormous elliptical paths that take them tens of thousands of years to complete. These clusters contain some of the oldest stars we know about. They formed when the universe was young, when conditions were completely different from what we see today. In a way, studying them is like archaeology, except instead of digging through dirt, we're digging through time itself, using light that's traveled for eons to reach us. But here's where things get really mysterious. All of this visible matter, all these ancient stars and spectacular clusters, they're actually just the tip of the iceberg. Surrounding everything we can see is this much larger halo made of something we call dark matter. We can't see it directly, but we know it's there because of how it affects the motion of stars and gas. Without this invisible dark matter halo, the outer regions of our galaxy should be rotating much more slowly than they actually are. It's like watching a figure skater spin, but instead of slowing down when they extend their arms, they somehow maintain the same speed. The only explanation is that there's a lot more mass out there than we can account for with visible matter alone. This dark matter halo is thought to extend several 100,000 light-years from the galactic center, possibly up to 1,000,000 light-years. That's absolutely enormous, dwarfing even the impressive size of the stellar halo. Most of our galaxy's mass actually comes from this invisible stuff, not from the stars and gas that we can actually see and photograph. It's humbling in a way, realizing that most of our cosmic neighborhood is made of something we don't understand, something we can't even directly detect. We're like people living in a house, but most of the house is made of invisible materials. We know the walls are there because we can't walk through them, but we can't actually see what they're made of. One of the strangest things about the halo is that it doesn't really have a defined edge. Unlike the galactic disk, which has a pretty clear boundary where the star density drops off dramatically, the halo just gradually fades away into intergalactic space. There's no cosmic fence post marking where our galaxy ends and empty space begins. Astronomers sometimes use something called the virial radius to define the galaxy's edge, which is basically the region where our galaxy's gravity dominates over the expansion of the universe itself. For the Milky Way, this comes out to somewhere between 250,000 and 300,000 light-years, though some models suggest even larger values. Within this vast halo, there are these ghostly streams of stars that trace the remains of past galactic meals. When a smaller galaxy gets too close to the Milky Way, tidal forces stretch it out like taffy, scattering its stars along these elongated paths that wrap around our galaxy. These stellar streams are incredibly faint, barely detectable against the background of space, but they tell the story of how our halo was built up piece by piece. The Sagittarius stream is probably the most famous example. It's the scattered remains of a dwarf galaxy that's currently being digested by the Milky Way, like cosmic leftovers spread across hundreds of thousands of light-years. These streams show that the halo isn't some static, unchanging structure. It's dynamic, still evolving, still being shaped by ongoing gravitational interactions. The stars in the halo are chemically different from the stars in the galactic disk. They're what astronomers call metal poor, meaning they don't contain much of the heavier elements that get produced by successive generations of supernovae. This suggests that many halo stars formed very early in cosmic history, before the galaxy had been enriched by multiple cycles of star formation and death. Some of these halo stars might even be older than the Milky Way itself, born in dwarf galaxies that were later absorbed into our growing galactic metropolis. Studying them gives us a window into the early universe, clues about what conditions were like billions of years ago when the cosmos was young and wild and very different from today. In this sense, the halo isn't just a boundary or a collection of old stars. It's a time capsule, preserving information about epochs so ancient that they predate most of the familiar structures we see in the modern universe. Every halo star is like a messenger from the deep past, carrying news from times when galaxies were smaller, space was more crowded, and cosmic evolution was just getting started. For those of us living in the galactic disk, the halo is incredibly easy to forget about. It's completely invisible to the naked eye, its stars too faint and spread out to make any impression on our night sky. Yet it surrounds us completely, extending in all directions, like we're living inside some enormous, mostly empty sphere. To really grasp the halo's presence, you have to think not of bright, obvious features, but of vast emptiness dotted with incredibly rare, ancient stars. It's the part of our galaxy that feels least like home and most like wilderness. And yet, surprisingly, it's still part of the same gravitational system that holds us. Its faint stars still orbit the galactic center, bound by the same fundamental forces that keep our solar system intact. The existence of the halo challenges our intuitive sense of where things end. If someone asks you where the Milky Way ends, your first instinct might be to point to the edge of the visible disk, but the halo shows that our galaxy actually stretches much, much farther than that. Even beyond what we can see, its gravitational influence extends into what we might otherwise think of as empty intergalactic space. This complicates the seemingly simple question of how big our galaxy actually is. If you only count the stars in the disk, you get one answer. If you include the stellar halo, you get a bigger number. If you include the dark matter halo, you get an even more impressive figure. Each definition yields a different boundary, and none of them is definitively correct. It depends on whether you're measuring light, stars, or gravitational influence. When we look at other galaxies, like our neighbor Andromeda, we can actually see this same pattern repeated. Andromeda has its own bright disk, surrounded by its own faint halo of stars and gas. That halo also extends hundreds of thousands of light years. And here's the really interesting part. It probably overlaps with our own Milky Way's halo. The two galaxies' halos may already be interacting, blurring the distinction between separate galactic systems long before their visible disks are scheduled to merge in the distant future. This overlap reinforces the idea that halos aren't just cosmic afterthoughts. They're essential components that shape how galaxies interact and evolve over cosmic time. The halo also has practical importance for understanding cosmology on the largest scales. By studying its stars and globular clusters, astronomers can refine their estimates of the Milky Way's total mass. This information is crucial for understanding our galaxy's role in the local group of galaxies and predicting the details of our eventual merger with Andromeda. The motions of halo stars provide constraints on how much dark matter actually surrounds us, which helps inform theoretical models of how structure formed throughout the universe. So the halo isn't just some cosmic curiosity, it's central to understanding how galaxies form and evolve across billions of years. Despite its importance, the halo remains deeply mysterious. We don't yet know the exact shape of the dark matter distribution that dominates it. Is it spherical, elongated, clumpy, smooth? We're still discovering new stellar streams, still trying to figure out exactly how many past mergers contributed to the halo's current structure. Each new astronomical survey reveals more complexity, suggesting that the halo is much less like a smooth sphere and much more like a tangled web of cosmic debris. It's simultaneously the most difficult part of our galaxy to study and the part that potentially tells us the most about our cosmic history. For anyone lying under a dark night sky, the halo remains completely invisible, but its effects are absolutely everywhere. The sun's orbit through the galaxy, the rotation of the galactic disk, even the survival of the spiral arm patterns we see in galaxy photos. All of these familiar features are made possible by the enormous mass contained in the halo. Without this invisible scaffolding of dark matter and ancient stars, the Milky Way simply wouldn't look the way it does. We might never notice the halo with our eyes, but we live our entire lives within its gravitational embrace, citizens of a cosmic structure far larger and more ancient than we can directly perceive. Picture yourself standing under a starlit sky, gazing up at the Milky Way stretching across the heavens. What you're seeing, those countless points of light, represents only a tiny fraction of what's actually there. The rest, the overwhelming majority, remains completely invisible to us. When scientists first started studying how stars move around in galaxies, they expected something fairly straightforward. Just like planets in our solar system, stars farther from the galactic center should move more slowly than those closer in. Mercury races around the Sun much faster than distant Neptune because the Sun's gravitational pull weakens with distance. This makes perfect sense, and astronomers figured galaxies would work the same way. But when they actually measured star speeds in the Milky Way, and in other galaxies too, something strange emerged. Stars on the outer edges weren't slowing down. like they should. Even way out there, far from the bright galactic center, these stars were whipping around at surprisingly high speeds. The only way this could happen was if there was much more mass present than anyone could see. This invisible mass, this hidden component of our galaxy, is what we now call dark matter. The name fits perfectly, because this stuff doesn't give off any light whatsoever. It doesn't glow, it doesn't reflect light, it doesn't absorb radiation. Nothing. We can't detect it directly through any form of electromagnetic radiation, yet its gravitational effects are absolutely undeniable. Think about what this means for our own galaxy. The Milky Way appears to be embedded within an enormous, invisible sphere of dark matter. This sphere, this halo, probably contains 10 times more mass than all the stars and gas clouds we can actually observe. 10 times more. That's a staggering amount of hidden material. Imagine the Milky Way as a glowing disk floating inside a vast transparent bubble. The disk contains all the stars, all the nebulae, everything that lights up the night sky. But the bubble, much larger and completely invisible, contains most of the actual mass. This bubble shapes how stars orbit, it holds distant star clusters in their proper places, and it even influences the paths of small companion galaxies that orbit around us. Without this dark matter halo, our galaxy would simply fly apart. The gravitational glue holding everything together would be insufficient. Stars would drift away into the void, and the beautiful spiral structure we call home would dissolve into chaos. In a very real sense, we owe our existence to something we cannot see. Scientists have spent decades trying to figure out what dark matter actually is. They know it's not made of ordinary atoms, the same stuff that makes up stars, planets, and us. If it were, we'd detect its presence through various forms of radiation or absorption patterns in starlight. Instead, dark matter seems to consist of exotic particles that barely interact with normal matter at all. Some researchers propose particles called WIMPs, weakly interacting massive particles. Others suggest axions, hypothetical particles that might solve several puzzles in physics simultaneously. But despite building incredibly sensitive detectors and conducting countless experiments, nobody has managed to catch a dark matter particle directly. It remains stubbornly elusive. The Milky Way serves as one of our best natural laboratories for studying this mysterious substance. By carefully tracking how stars move at different distances from the galactic center, astronomers can map out the shape and size of our dark matter halo. These studies suggest the halo extends hundreds of thousands of light years outward far beyond the visible disk, gradually blending into the halos of neighboring galaxies like Andromeda. This overlap reveals something profound about the cosmos. Galaxies aren't isolated islands, floating in empty space. They're connected through their dark matter envelopes, part of a vast cosmic web that spans the observable universe. The boundaries between galaxies become fuzzy when you consider their invisible components. Stellar streams provide another fascinating clue about dark matter's distribution. When small galaxies venture too close to the Milky Way, our galaxy's gravity tears them apart, stretching their stars into long, trailing ribbons. The exact paths these stellar streams follow depend on how dark matter is distributed throughout our galactic halo. By mapping these streams, astronomers can determine whether the halo is smooth or lumpy, round or elongated. Each stream acts like a tracer particle in an invisible fluid, revealing the hidden currents of gravity that surround us. It's remarkable that we can deduce so much about something we can't see directly simply by watching how visible objects respond to its presence. Computer simulations help us visualize what this hidden universe might look like. When researchers model cosmic evolution using dark matter, they produce structures that match what we observe remarkably well. Filaments of dark matter stretch across vast distances, with galaxies forming like pearls, strung along these invisible threads. Enormous voids open up between the filaments, creating the cosmic web we see today. In this picture, dark matter isn't just an add-on to an existing universe. It's the fundamental scaffolding upon which everything else is built. Without dark matter, galaxies might never have formed in the first place. The early universe would have remained a smooth, featureless expanse of hydrogen and helium gas, our own existence depends on dark matter in ways we're only beginning to appreciate. The Milky Way formed because dark matter clumped together first, creating gravitational wells that pulled in normal matter. This allowed gas clouds to collapse and form the first stars. The invisible halo didn't just shape our galaxy's past, it continues to govern its present and future. Living inside this dark matter halo means we're completely surrounded by something we cannot directly perceive. You can't touch dark matter, you can't see it, you can't feel it passing through your body, even though it probably is. Yet every motion of our solar system around the galaxy is influenced by this invisible presence. Our orbital speed, the stability of the galactic disk, the persistence of spiral arms, all depend on unseen mass. When you step outside on a clear night and look up at the stars, you're viewing a display made possible by dark matter, even though none of that dark matter contributes a single photon to the spectacle. The phrase ghostly glow captures this paradox perfectly. Dark matter reveals itself indirectly, like a ghost whose presence is felt but never seen. The glow isn't luminous, it's gravitational. This ghostly nature makes dark matter all the more mysterious. Every experiment designed to detect it directly has come up empty-handed. Scientists have built incredibly sensitive detectors, buried them deep underground to shield them from interference, and waited patiently for rare collisions between dark matter particles and ordinary atoms. Other researchers have searched for telltale radiation signatures that might indicate dark matter particles destroying each other in space. So far, nothing definitive has emerged. The mystery deepens with each failed detection attempt, yet the gravitational evidence remains absolutely overwhelming. We live inside a cosmic puzzle where most of the mass is invisible. The stars, gas clouds, and dust that make up the visible Milky Way represent only the tip of an enormous iceberg. The dark matter halo is the hidden bulk, unseen but fundamental to everything we experience. This realization changes how we think about our place in the universe. When we ask how large the Milky Way really is, the answer depends heavily on whether we include its dark matter halo. If we do, our galaxy's reach extends far beyond the visible disk, perhaps 5 or 10 times larger in radius than what we can observe directly. Dark matter also shapes our galaxy's future in profound ways. The eventual collision between the Milky Way and Andromeda, predicted to occur in several billion years, won't just involve stars and gas clouds. The dark matter halos of both galaxies will merge as well. In fact, these invisible components are probably already interacting. Even though the visible portions of the galaxies are still millions of light years apart, long before any stars actually collide, the dark matter halos will begin their cosmic dance, setting the stage for one of the most spectacular events in our local corner of the universe. The choreography of this future merger is being written right now by invisible forces we can barely comprehend. On smaller scales, dark matter affects the delicate ecosystem of dwarf galaxies that orbit the Milky Way. Some of these tiny galaxies appear to be almost entirely composed of dark matter, with very few visible stars. Their fragile structures, easily disrupted by tidal forces, yet their survival depends on the protective cushioning of their own dark matter halos. These dwarf galaxies serve as both companions and scientific instruments. Their orbits trace the gravitational field created by our galaxy's dark matter halo, providing crucial data about its structure and extent. Each orbiting dwarf acts like a test particle in a vast physics experiment, revealing the invisible architecture that surrounds us. Even globular clusters, those ancient spherical collections of stars that populate our galaxy's halo, provide hints about dark matter's distribution. Though less dominated by dark matter than dwarf galaxies, their precise motions help astronomers refine estimates of the Milky Way's total mass. Current calculations suggest our galaxy weighs about 1.5 trillion times as much as our Sun, with most of that mass locked away in dark matter. This enormous mass places the Milky Way among the more substantial members of our local group of galaxies, though we're still smaller than Andromeda. It's humbling to realize that our cosmic neighborhood is dominated by mass we cannot see, cannot touch, and do not yet understand. Dark matter also complicates our attempts to define where the galaxy ends. Unlike stars, which eventually thin out to nothing, dark matter may extend smoothly and indefinitely outward, its density gradually decreasing with distance, but never quite reaching zero. There's no sharp boundary, no clear edge where the galaxy stops and empty space begins. This means that defining our galaxy's limits becomes somewhat arbitrary. Do we draw the line at some conventional distance where the density drops below a certain threshold? Or do we acknowledge that the halo extends even farther, gradually blending into the intergalactic medium? The ghostly glow of dark matter has no firm boundary. It simply fades until it becomes indistinguishable from the cosmic background. For the human imagination, dark matter represents both an unsettling challenge and a source of endless fascination. To discover that we live in a galaxy where most of the mass is completely invisible forces us to question our most basic assumptions about reality. We're accustomed to trusting our senses, particularly our vision, but here our eyes reveal only a small fraction of the truth. The rest must be inferred, deduced from subtle gravitational effects and orbital mechanics. It's a humbling reminder that the universe is far stranger and more complex than our everyday experience might suggest. We're surrounded by mystery on the grandest possible scale. Yet the evidence for dark matter's existence is rock solid. Every stellar orbit, every rotation curve, every galactic collision confirms its presence. The ghostly glow may not shine with visible light, but it permeates our cosmic neighborhood, shaping our galaxy's structure and determining our fate. In learning to see the invisible, we've discovered that reality extends far beyond the reach of our senses, into realms that challenge our understanding and inspire our wonder. Far above and below our galaxy's familiar disk, ancient stellar cities drift through space in long sweeping paths. These globular clusters, as we call them, are among the oldest structures in the Milky Way, carrying within their densely packed cores the memories of cosmic youth. Picture hundreds of thousands, sometimes millions of stars, all squeezed into a sphere just a few dozen light years across. Through a telescope, they appear as glittering balls of light, each point representing a sun nearly as old as the universe itself. The density is almost unimaginable, with stars separated by mere fractions of a light year, while here in our neighborhood, the nearest star sits more than 4 light years away. These stellar congregations follow orbits that tell stories of disruption and capture. Unlike the orderly rotation we see in the galaxy's disk, many globular clusters travel on tilted, elongated paths, suggesting they arrived here through more chaotic means. Some formed alongside our galaxy in its earliest epochs, while others may be the captured remnants of smaller galaxies that wandered too close and were absorbed into the Milky Way's gravitational embrace. The ages of these clusters inspire a certain cosmic humility. Most range between 10 and 13 billion years old, meaning they formed when the universe was still young and galaxies were just beginning to take shape. Their stars are what astronomers call metal poor, containing very little of the heavier elements we take for granted, elements like carbon, oxygen, and iron that were forged in later stellar generations. This chemical simplicity makes globular clusters natural laboratories for understanding early cosmic evolution. By studying their light, astronomers can trace how quickly our galaxy enriched itself with the building blocks of planets and ultimately life itself. Each spectrum tells part of the story of how raw hydrogen and helium transformed into the complex chemistry that surrounds us today. The stability of these ancient clusters is remarkable. While younger, looser star groups in the disk eventually drift apart after a few 100 million years, globular clusters maintain their tight gravitational bonds for billions of years. Their dense cores act like cosmic glue, holding them together even as the galaxy's tidal forces stretch and tug at their outer edges. Some clusters do show signs of this gravitational harassment, trailing streams of escaped stars behind them as they orbit. These stellar streams become breadcrumbs that help astronomers trace the invisible architecture of dark matter surrounding our galaxy. In this way, globular clusters serve not just as ancient relics, but as active probes mapping the unseen scaffolding of space. The wanderings of these clusters extend far beyond the galaxy's visible edges, with some reaching distances of more than 100,000 light-years from the center. They mark the true extent of our cosmic home, showing us that the Milky Way's gravitational influence stretches far beyond what spiral arms alone might suggest. The outermost clusters orbit near the boundary where our galaxy's halo begins to blend with the vast emptiness between galaxies. Among these ancient wanderers, some stand out for their peculiar properties. Omega Centauri, the largest cluster in our galaxy, contains millions of stars and may not be a typical cluster at all. Its stars show a wider range of ages and compositions than most, suggesting it might be the surviving core of a dwarf galaxy consumed long ago. If true, it represents both a stellar cluster and a fossil galaxy, a tangible reminder that growth often comes through consumption. The extreme stellar density within these clusters creates environments unlike anything in our cosmic neighborhood. Stars crowd so closely together that interactions become commonplace, close encounters that can result in binary exchanges, stellar mergers, and even direct collisions. These cosmic accidents produce exotic objects like blue stragglers, stars that appear younger and hotter than their cluster companions, rejuvenated through merger or by siphoning material from nearby stars. From the perspective of potential life, these dense, stellar neighborhoods present fascinating puzzles. The crowded conditions might make planetary systems unstable, with close encounters disrupting the delicate orbital dance that allows worlds to form and persist. Yet the sheer abundance of stars also creates numerous opportunities for habitable planets to exist. Whether life could thrive in such densely packed regions remains an open question, but the possibility adds another layer to our understanding of where biology might take hold in the universe. Perhaps somewhere in those glittering cores, worlds orbit ancient suns under skies, blazing with the light of countless stellar neighbors. For astronomers studying cosmic distances, globular clusters serve as valuable measuring sticks. They commonly host variable stars whose predictable brightness changes, allow precise distance calculations. These stellar lighthouses help calibrate the cosmic distance ladder, refining our maps of both the Milky Way and the broader universe beyond. Our galaxy hosts around 150 known globular clusters, though more likely remain hidden by dust near the galactic center. Other galaxies possess their own collections, with Andromeda harboring several hundred. The number of clusters a galaxy contains relates to its mass and merger history, providing another tool for comparing galactic evolution across the cosmos. These ancient stellar cities remind us that our galaxy is not uniform, but rather a complex layered structure where different components tell different chapters of cosmic history. The disk speaks of ongoing star formation and chemical enrichment, while the globular clusters whisper tales of the universe's youth, when the first stellar generations lit up the primordial darkness. In their endless orbits through the halo, these clusters serve as both wanderers and anchors, marking the galaxy's true extent while connecting us to deep time. They represent a kind of cosmic continuity, survivors from an era when the universe was fundamentally different, yet still bound by the same gravitational forces that shape our cosmic neighborhood today. Each cluster carries encoded memories of ancient events, merger histories written in stellar positions and chemical compositions. By studying their properties and orbits, astronomers can reconstruct the assembly history of our galaxy, piecing together the collisions and accretions that built the halo we observe today. These stellar witnesses continue their patient dance around the galaxy, billions of years after their formation, carrying within their ancient light the stories of cosmic youth and the long, slow process by which chaos gave way to the structured universe we inhabit today. Our galaxy floats in an ocean that most people never think about. While we focus on the brilliant points of starlight scattered across the night sky, the real story happens in the spaces between. Vast quantities of gas drift through these regions, invisible to our eyes but absolutely crucial to everything we see. This gas exists everywhere, filling what we used to think was empty space. It gathers in enormous clouds, some stretching hundreds of light years across. These aren't the fluffy white clouds we know from Earth's sky. They're made mostly of hydrogen, with some helium mixed in, and they're so thin that breathing them would be impossible. Yet these gossamer structures hold incredible power. When gravity pulls them together, They collapse into dense knots. These knots heat up, ignite, and become new stars. Every star in our galaxy, including our Sun, was born this way from drifting gas clouds. The process takes millions of years to unfold. A cloud drifts through space, perhaps disturbed by a nearby explosion or collision with another cloud. Slowly, inexorably, parts of it begin to contract. The hydrogen atoms that were once spread across vast distances find themselves drawn together by their own collective gravity. Deep within these forming stellar nurseries, temperatures and pressures climb. When conditions reach a critical point, nuclear fusion begins. A new star switches on, flooding the surrounding area with intense radiation and powerful winds. This birth announcement changes everything around it. The newborn star's energy ionizes nearby gas, causing it to glow in brilliant colors. We see these regions as nebulae, glowing patches scattered throughout our galaxy's spiral arms. The Orion Nebula represents one of these cosmic maternity wards. Visible to the naked eye as a fuzzy patch, it's actually a massive stellar factory where dozens of new suns are taking shape. The beautiful colors we see in photographs come from different gases glowing under intense stellar radiation. But stars don't just form from gas, they also destroy it. Young, hot stars blast their surroundings with radiation and stellar winds. These forces carve out enormous bubbles in the surrounding medium, pushing gas away and heating it to incredible temperatures. When massive stars reach the end of their lives, they explode as supernovae. These explosions send shock waves racing through nearby gas clouds, disrupting their structure and heating them to millions of degrees. The blast can completely dissolve the cloud that originally gave birth to the star. This creates a fascinating cycle. Gas condenses into stars, stars disrupt gas clouds, and the dispersed material eventually gathers again into new clouds elsewhere. The galaxy constantly recycles its raw materials, ensuring that star formation can continue for billions of years. Radio telescopes allow us to map this invisible medium across our entire galaxy. Hydrogen gas emits radio waves at a very specific wavelength, 21 centimeters. By detecting this emission, astronomers can trace the distribution of gas even in regions where dust blocks our view of stars. These radio maps reveal that gas extends far beyond the bright spiral arms we see in optical images. The gaseous disk of our galaxy stretches much farther into space than the stellar disk. In the outer regions where few stars shine, vast amounts of gas continue drifting through the darkness. The story becomes even more remarkable when we consider the galaxy's halo. Surrounding our entire galaxy is an enormous envelope of hot, diffuse gas. This circumgalactic medium extends hundreds of thousands of light years from the galactic center, nearly filling the dark matter halo itself. We can't see this halo gas directly, but we detect it through clever observations. When light from distant quasars passes through our galaxy's halo, the gas absorbs specific wavelengths. These absorption lines tell us about the temperature, density, and composition of gas we could never image directly. The halo contains as much gas as the entire galactic disk, possibly more. This represents an enormous reservoir of future star formation material. Gas slowly flows inward from the halo, feeding star formation in the spiral arms. At the same time, supernovae and stellar winds push processed material back outward into the halo. This circulation system regulates the galaxy's metabolism. Without the halo reservoir, star formation would quickly exhaust the available gas supply. The galaxy would grow old and quiet, with no new stars to replace those that burn out and die. The continuous cycling of material means that boundaries become difficult to define. Stars exist as discrete objects we can count and catalogue. Gas, however, forms a continuous medium that gradually thins out with distance. The galaxy doesn't end abruptly, it fades slowly into the intergalactic void. These processes operate on scales that challenge human imagination. A single molecular cloud might contain millions of times the mass of our Sun. The circumgalactic medium holds tens of billions of solar masses in its tenuous embrace. Gas clouds, larger than our entire solar system, drift slowly through space, taking millions of years to cross from one side of the galaxy to the other. The atoms in our bodies participated in this grand circulation long before Earth formed. The carbon in our cells, the oxygen we breathe, the iron in our blood, all were forged inside ancient stars. When those stars died, they expelled their processed elements into the interstellar medium. These atoms drifted in gas clouds for perhaps hundreds of millions of years before gravity gathered them into the nebula that would become our solar system. The calcium in our bones was once part of a diffuse cloud floating between the stars. Every element heavier than hydrogen has this biography, this journey through the cosmic recycling system. Gas clouds also create many of the dark patches we see when we look up at the Milky Way on a clear night. These aren't empty regions, they're dense clouds blocking the light of stars behind them. The famous Horsehead Nebula appears dark, not because nothing is there, but because so much material is there that it obscures the stellar background. Modern astronomy uses multiple techniques to study this invisible medium. Radio telescopes map cold hydrogen gas. Infrared observations reveal warm dust mixed with the gas. X-ray telescopes detect the hot bubbles carved out by stellar explosions. Ultraviolet spectroscopy probes the circumgalactic halo. By combining all these observations, we construct a picture of our galaxy as a dynamic, living system. Gas flows in complex patterns, cycling between different phases and temperatures. Material constantly moves between the disk and halo, between dense clouds and diffuse regions. This perspective transforms our understanding of cosmic evolution. Galaxies aren't simply collections of stars, they're ecosystems with intricate flows of matter and energy. The gas that drifts invisibly through space today will become the stars that shine billions of years in the future. The timescales involved dwarf human experience, yet the processes continue all around us. While we sleep, vast clouds of hydrogen drift slowly through the galaxy. While we go about our daily lives, gravity pulls these clouds together in distant regions of space. While we age and pass our lives, new stars ignite in stellar nurseries we'll never see. This ongoing cycle connects us to the cosmos in the most literal way possible. We are made of processed stellar material, temporarily organized into conscious beings, destined eventually to return to the cosmic circulation. The boundary between ourselves and the drifting gas clouds becomes philosophical rather than physical when viewed from this perspective. When you imagine our galaxy, you probably picture bright stars scattered through dark space, maybe some glowing clouds of gas here and there. But there's something else threading through the entire Milky Way, something completely invisible yet surprisingly important. Magnetic fields stretch across our galaxy, weaving through everything like cosmic spider silk. These galactic magnetic fields are incredibly weak, thousands of times weaker than the little magnet holding your grocery list to the refrigerator. Yet their influence spans distances that would take light thousands of years to cross. It makes you wonder how many invisible forces surround us, every day, shaping our world in ways we never notice. The magnetic field of our galaxy doesn't look anything like the neat, simple field around Earth, with its clear north and south poles. Instead, imagine tangled yarn that's been twisted and pulled and stretched across unimaginable distances. The field follows a rough spiral pattern, sort of matching the galaxy's spiral arms, but it's also full of loops and knots and chaotic tangles. Supernova explosions twist these magnetic threads into new patterns. Stellar winds from massive stars bend and reshape them constantly. The rotation of our entire galaxy slowly winds them up over millions of years. It's like watching an invisible sculpture that never stops changing, carved by forces beyond our everyday experience. Scientists have clever ways of detecting these hidden fields, even though we can't see them directly. Dust grains floating in space actually line up with magnetic field lines, like tiny compass needles. When starlight passes through this aligned dust, it becomes polarized, meaning the light waves start vibrating in one specific direction, instead of randomly. Radio waves from distant sources get twisted as they travel through magnetized gas, a process called Faraday rotation. By measuring how much the radio waves twist, astronomers can figure out where magnetic fields exist and how strong they are. It's remarkable that we can map invisible structures spanning our entire galaxy using such indirect clues. Much of the gas floating between stars isn't neutral atoms like you might expect. It's ionized plasma, where electrons have been stripped away from their parent atoms. These free charged particles respond to magnetic fields in fascinating ways, spiraling around invisible field lines, like cars following curved highways. This relationship between magnetic fields and charged particles affects star formation in profound ways. When a cloud of gas starts collapsing under its own gravity to form new stars, magnetic fields can slow down the process. They resist compression in some directions while allowing it in others, essentially controlling how and where new stars are born. The fields can also launch powerful outflows from young stars, shooting material back into space at incredible speeds. Every new star in our galaxy has been influenced by these invisible magnetic threads during its formation. Without them, the process of star birth would unfold completely differently. Cosmic rays, those high-energy particles racing through space at nearly light speed, owe their journey to galactic magnetic fields. When supernovas explode, or other violent events accelerate particles to extreme energies, the magnetic fields keep them trapped within our galaxy instead of letting them escape into empty intergalactic space. These cosmic ray particles bounce around our galaxy for millions of years, following magnetic field lines like pinballs in a cosmic machine. Every cosmic ray that eventually strikes Earth's atmosphere has been shepherded by the Milky Way's magnetic field, traveling paths we could never trace, but that connect us to distant, stellar explosions. The magnetic threads extend far beyond the visible disk of our galaxy, reaching out into the halo where dark matter dominates. Hot, diffuse gas fills this region, and magnetic fields thread through it as well. Some evidence suggests these fields might stretch hundreds of thousands of light-years from the galactic center, possibly even connecting with magnetic fields from neighboring galaxies. This creates a puzzling question about where our galaxy actually ends. If magnetic fields extend that far out, linking with the broader cosmic web of matter, then the Milky Way isn't really an isolated island in space. It's more like part of an interconnected network stitched together by invisible forces. Nobody knows exactly how these galactic magnetic fields formed in the first place. One idea involves tiny seed fields that existed in the very early universe, somehow getting amplified over billions of years. The rotation of our galaxy and the turbulence from countless supernova explosions might have gradually strengthened and organized these fields into the patterns we observe today. This process, called a galactic dynamo, operates on scales vastly larger than anything we experience on Earth. It sustains magnetic fields across our entire galaxy for billions of years, creating and maintaining an invisible infrastructure that's just as important as gravity for holding everything together. The existence of these magnetic fields blurs the boundaries of what we consider our galactic home. We typically think of the Milky Way as having some kind of edge, a place where it stops and intergalactic space begins. But magnetic fields don't respect such neat boundaries. They fade gradually, rather than stopping abruptly, connecting our galaxy to the larger cosmic web in ways that challenge our sense of separation. Living inside this vast magnetic web, we never directly experience its presence, yet it influences everything around us. The cosmic rays reaching Earth, the star formation happening in distant nebulae, even the overall structure of interstellar space, all bear the invisible fingerprints of galactic magnetism. It's humbling to realize that forces completely beyond our perception shape the cosmic environment we call home. These magnetic threads remind us that the universe operates on principles and scales that stretch our imagination, creating order and structure through mechanisms we're only beginning to understand. The more we learn about galactic magnetic fields, the more they seem to dissolve the concept of clear boundaries in space. Instead of distinct objects with definite edges, galaxies become part of a continuous interconnected web where invisible forces matter just as much as the bright stars we see in the night sky. The numbers we throw around for the Milky Way's size, like 100,000 light-years across, give us a false sense of certainty. These measurements feel precise, but they're really just educated guesses based on arbitrary lines we've drawn in space. The universe doesn't deal in sharp boundaries the way our minds prefer to organize things. When you think about it, galaxies are nothing like the familiar objects we know on Earth. They don't have coastlines like continents, or walls like buildings. Instead, they just slowly fade away, like the edge of a campfire's glow disappearing into darkness. Star density decreases bit by bit. Gas clouds become thinner and thinner, until eventually you can't tell where the galaxy ends and empty space begins. The spiral arms we picture in textbooks don't just stop at some invisible fence. They peter out gradually, with stars becoming more and more scattered as you move outward. Observations suggest a stellar disk reaches maybe 100,000 light-years in diameter, possibly more. But even this measurement depends on where you decide to stop counting stars. Beyond the main disk, there's still the halo, a vast spherical region filled with older stars wandering in elongated orbits. These stars are definitely part of the Milky Way, but they're spread so thin that defining an outer boundary becomes almost meaningless. You can't point to any single star and declare it the absolute last member of our galaxy. Gas complicates the picture even further. The cold molecular clouds where new stars are born stay mostly within the inner regions, maybe tens of thousands of light-years from the galactic center. But atomic hydrogen gas extends much farther out, well beyond where the visible stars fade away. And hot, ionized gas fills something called the circumgalactic medium, stretching hundreds of thousands of light-years in all directions. If we measured the galaxy based on where its gas reaches, rather than just its stars, the Milky Way would be enormously larger. But again, there's no clear cutoff, just a gradual thinning until the density becomes indistinguishable from the space between galaxies. Dark matter makes everything even more complicated. Its halo probably extends close to 1 million light-years across, overlapping with the dark matter from neighboring galaxies, like Andromeda. If you defined the Milky Way by its dark matter, you'd find it nearly impossible to say where our galaxy ends and others begin. The gravitational influence of each galaxy blends into the others, long before their visible parts will eventually collide. Billions of years from now, this overlap challenges our basic idea of what makes one galaxy distinct from another. We like to think of galaxies as separate islands in space, but they're more like overlapping spheres of influence, each fading gradually into the cosmic web that connects everything. Even within the galaxy itself, boundaries remain fuzzy. The central bulge doesn't have a clear border where the disk suddenly takes over. Stellar populations mix and overlap, with different types of stars scattered throughout various regions. The disk doesn't abruptly give way to the halo either. Instead, there's just a gradual change in how stars move and how densely they're packed together. Think of the galaxy as a system of layers, like an onion, except the layers aren't neatly separated. They blend into each other, each one fading gradually into the next, creating a continuous gradient rather than distinct zones. For astronomers trying to build models and make measurements, this fuzziness creates real practical problems. Where do you stop counting stars? At 120,000 light-years out? Or 200,000? Do you include all the gas in the circumgalactic medium? What about tidal streams from small dwarf galaxies that are being torn apart by the Milky Way's gravity? These streams are technically gravitationally bound to our galaxy, but they didn't originate here. The answers vary depending on what you're studying and why. That's why textbook estimates of the Milky Way's size range anywhere from 100,000 to 200,000 light-years or more. None of these numbers are wrong, but none of them tell the complete story either. They're all based on different definitions of where to draw that arbitrary line. This pattern isn't unique to our galaxy. When we observe Andromeda, we see a bright central region surrounded by spiral arms, but deep observations reveal faint halos of stars stretching much farther out. These outer regions contain streams of stars from smaller galaxies that Andromeda has consumed over billions of years, plus diffuse starlight that fades gradually into the background. Elliptical galaxies show the same behavior, with their outer regions gradually fading away rather than ending abruptly. The universe seems to prefer gradual transitions over sharp edges, creating gradients of density that blur one system into the next. From our human perspective, this ambiguity can feel both frustrating and oddly freeing. We want clear answers to simple questions like, how big is the Milky Way? Or, where does it end? But nature doesn't conform to our desire for neat categories and precise boundaries. Reality is messier, more continuous, more nuanced than our mental models suggest. The galaxy isn't a closed system with walls keeping everything inside. It's an open system constantly exchanging matter and energy with its surroundings, blending gradually into the cosmic web that connects all galaxies across the universe. This openness changes how we might think about our cosmic home. If the galaxy doesn't have clear edges, then our home doesn't either. It extends gradually outward, fading into intergalactic space, while remaining connected to the broader universe in ways we're still discovering. Belonging to the Milky Way becomes less about living inside some defined boundary, and more about being part of a gradient, a continuum of matter and gravitational influence that reaches out indefinitely. We're not enclosed within walls, but embedded in a gradual transition from dense to sparse, from organized to chaotic. Astronomers sometimes use the concept of gravitational dominance to define practical boundaries. The virial radius, for example, marks the distance where the galaxy's gravity is just strong enough to hold matter together against the expansion of the universe itself. For the Milky Way, this distance is roughly 250,000 to 300,000 light-years from the center. Beyond that radius, the galaxy's gravitational pull becomes weaker than the general expansion of space, so matter tends to get carried away rather than staying bound to the galaxy. This provides a useful working definition, but it's still not a wall or barrier. Matter doesn't suddenly stop feeling the Milky Way's influence at that exact distance. The gravitational gradient continues, just getting weaker and weaker. These blurred edges become especially apparent when we look at the galaxy's interactions with its neighbors. The Magellanic Clouds, those two small galaxies visible from the southern hemisphere, orbit around the Milky Way like cosmic satellites. They're separate systems with their own stars and gas, yet they're connected to us by long streams of material pulled out by gravitational tides. These streams, called the Magellanic Stream and Leading Arm, stretch across huge portions of the sky, linking the dwarf galaxies to the Milky Way's halo. Are these streams inside our galaxy or outside it? The answer depends entirely on how you choose to define the boundary. They're companions, yet also part of our extended system, their material gradually mixing with ours over cosmic time. Tidal streams from past mergers tell similar stories. The Sagittarius dwarf galaxy is currently being torn apart by the Milky Way's gravity, its stars stretched into long arcs that wrap around our galaxy multiple times. These streams are technically part of our halo now, but they originated as a completely separate galaxy. Are they the edge of the Milky Way, or the remnant of something else entirely? Again, the boundary becomes meaningless. Our galaxy grows by gradually absorbing smaller neighbors, and its edges are defined not by fixed limits, but by ongoing interactions that play out over hundreds of millions of years. For scientists, thinking in terms of gradients rather than boundaries opens up new ways of understanding galactic structure. Instead of asking where the galaxy ends, we ask how it fades, how density and composition and gravitational influence change with distance from the center. These gradients contain the historical record of how the galaxy formed and evolved. The distribution of different types of stars tells us about past episodes of star formation. The chemical composition of gas clouds reveals how elements created in stellar cores have spread throughout the galaxy over billions of years. The dark matter distribution shows us the underlying scaffold that holds everything together. When we lie under a dark night sky and look up at the bright band of the Milky Way stretching overhead, those gradients are invisible to our eyes. We see what appears to be a fixed structure, a celestial river of light with definite edges where it fades into the surrounding darkness. But in reality, that bright band represents only the densest part of a much larger system that extends far beyond what we can see. The true edges of our cosmic home are not edges at all, but gentle transitions that remind us how the universe prefers continuity over sharp divisions, gradients over boundaries, connection over separation. The universe operates on a principle that seems to govern everything from human societies to cosmic structures. Gravity naturally draws things together, rather than keeping them apart. When we think about our home galaxy, we might imagine it as this solitary island floating in the darkness of space, but that image couldn't be further from reality. The Milky Way exists within what astronomers call the local group, a modest neighborhood of galaxies that might seem small compared to the massive galaxy clusters scattered throughout the cosmos. Yet this local group represents the entire accessible universe for civilizations, like ours, at least for the foreseeable future. Within this cosmic neighborhood, the Milky Way plays the role of the dominant partner. Its hundreds of billions of stars and vast invisible halo of dark matter exerting influence far beyond what we might expect. The most familiar neighbors are probably the large and small Magellanic Clouds, two irregular dwarf galaxies that appear as fuzzy patches of light in southern skies. These cosmic companions are close enough that ancient peoples could see them without any optical aid, though they likely had no idea they were looking at entire galaxies. The Magellanic Clouds dance around our galaxy in complex orbital patterns, their paths influenced not just by the Milky Way's gravity, but also by their gravitational relationship with each other. What makes these interactions particularly fascinating is how messy they are. The Magellanic Clouds don't orbit the Milky Way like neat, well-behaved planets circling a star. Instead, tidal forces, the same type of gravitational effects that create ocean tides on Earth, stretch and pull at these smaller galaxies. Gas gets stripped away from the clouds, forming what's called the Magellanic Stream, a river of hydrogen that stretches across huge portions of the sky. This streaming gas represents something profound about how galaxies work. They're not closed systems with clear boundaries, like countries on a map. Instead, they're more like cities that gradually fade into suburbs, then into countryside, with no clear line where one ends and another begins. The Magellanic Stream shows us that our galaxy is actively feeding on its neighbors, growing through a process that's both violent and beautiful. Beyond the Magellanic Clouds, dozens of smaller dwarf galaxies orbit the Milky Way at various distances. Some of these are so faint, they're barely distinguishable from large star clusters. Others contain their own populations of young and old stars, complete with gas clouds where new stars might still be forming. These dwarf satellites demonstrate just how far the Milky Way's gravitational influence extends, reaching out thousands of light years to capture and hold these smaller systems. But here's where the story becomes particularly dramatic. Many of these dwarf galaxies are not permanent members of our cosmic family. They're slowly being torn apart by the very forces that keep them in orbit around us. The Sagittarius dwarf galaxy provides one of the most spectacular examples of this cosmic cannibalism. Discovered only in the 1990s, this galaxy is currently being shredded by the Milky Way's gravity, its stars pulled into long streams that wrap around our entire galactic halo. These tidal streams serve as archaeological evidence of our galaxy's growth through merger and acquisition. Each small galaxy that ventures too close eventually becomes part of the Milky Way, its stars scattered throughout our halo, its gas potentially fueling new generations of star formation. In this sense, our galaxy grows much like a city that gradually absorbs surrounding towns, incorporating their populations and resources into a larger whole. The relationship isn't entirely one-sided, though. While the Milky Way consumes its smaller neighbors, these companions also influence our galaxy's structure. The gravitational pull of the Magellan Clouds may actually warp our galaxy's disk, creating ripples and bends in what we once thought was a perfectly flat spiral structure. Recent observations suggest that the outer regions of the Milky Way's disk are indeed warped, possibly as a result of these ongoing interactions. The gas flowing in from the Magellanic Clouds and other neighbors doesn't just disappear when it reaches the Milky Way. Instead, it provides fresh material for star formation, like rain feeding a garden. Our galactic neighbors aren't just passive victims being consumed by a larger predator. They're active participants in shaping our galaxy's evolution, contributing to its growth and influencing its structure in ways we're still discovering. The local group contains another major player that will fundamentally reshape our cosmic neighborhood's future. The Andromeda Galaxy, larger than the Milky Way, with perhaps twice as many stars, currently sits about 2.5 million light-years away. But Andromeda isn't staying put. It's moving toward us at a considerable speed, and in roughly 4 billion years, these two galactic giants will collide. This future merger represents one of the most significant events in our galaxy's destiny. Long before the visible disks of stars actually overlap, the extended halos of dark matter and gas surrounding both galaxies will begin to interact. In some sense, the merger process has already begun, with the outermost reaches of both galaxies slowly blending together across the vast space between them. Other members of the local group will also play roles in this cosmic drama. The Triangulum Galaxy, smaller than both the Milky Way and Andromeda, but still substantial, appears to be gravitationally bound to Andromeda and may participate in the eventual merger. Even the faintest dwarf galaxies, some discovered only in recent years through sensitive surveys, orbit on the fringes of our galactic system, their motions influenced by the complex gravitational dance of the larger players. For astronomers, these galactic interactions provide natural laboratories for studying how galaxies evolve over cosmic time. By mapping the tidal streams left behind by disrupted dwarf galaxies, tracking gas flows between neighboring systems, and measuring the orbital motions of our companions, researchers can infer the distribution of invisible dark matter and estimate the total mass of the Milky Way. These neighboring galaxies essentially serve as test particles in a grand experiment, their movements tracing out the invisible scaffolding of dark matter that holds the entire local group together. Without these natural probes, our understanding of our own galaxy's structure and extent would be far more limited. On a philosophical level, these ongoing interactions remind us that galaxies, like all complex systems in the universe, are not static monuments, but dynamic, evolving entities constantly shaped by their relationships with their neighbors. The Milky Way we observe today is the product of billions of years of mergers, encounters, and exchanges with other galaxies. The Milky Way of the future will be dramatically different, transformed by ongoing interactions we can observe happening right now. When we step outside on a clear night and look up at the stars, most of what we see belongs to our own galactic disk. The Magellanic Clouds are visible only from certain latitudes, and the dwarf galaxies remain invisible without powerful telescopes. Even Andromeda appears as just a faint smudge of light that's easy to overlook if you don't know where to look. Yet these barely visible companions are as much a part of our cosmic story as the brilliant band of the Milky Way stretching across the sky. They remind us that our galaxy doesn't exist in isolation, but as part of a complex community of gravitationally interacting systems. The true extent of the Milky Way isn't defined just by its own stars and gas, but by the reach of its gravitational influence and its ongoing relationships with its cosmic neighbors. When you look up at the night sky from the southern hemisphere, two fuzzy patches of light catch your eye. These aren't stars, they're entire galaxies. The large and small Magellanic Clouds have been hanging there, visible to anyone who bothers to look up, for as long as humans have existed. People have been telling stories about these cosmic neighbors for thousands of years, long before anyone understood what they really were. There's something profound about that, how these distant worlds have been part of human consciousness, woven into myths and legends. Without us even knowing, we were looking at galaxies. The Large Magellanic Cloud sits about 160,000 light-years away from us. That might sound impossibly far, but in cosmic terms, it's practically next door. This galaxy contains tens of billions of stars, making it one of the more substantial dwarf galaxies we know about. Its smaller companion, the Small Magellanic Cloud, holds a few billion stars and sits even further out, at about 200,000 light-years. These aren't just random neighbors drifting through space. They're locked in an intricate gravitational dance, not just with our Milky Way, but with each other. The three of us, if you will, are engaged in this cosmic choreography that's been going on for billions of years. What makes this dance so fascinating is how violent and gentle it is at the same time. The gravitational forces involved are constantly pulling gas and stars away from the Magellanic Clouds. This creates something called the Magellanic Stream, this incredible ribbon of hydrogen gas that stretches across more than 100 degrees of sky. You can't see it with your eyes, but radio telescopes pick it up easily. Think about that for a moment. There's this massive stream of material, invisible to us, connecting our galaxy to these distant neighbors. It's like discovering that your house and your neighbor's house are connected by some invisible thread you never knew existed. Inside the Large Magellanic Cloud, there's this region called the Tarantula Nebula. It's the most active star-forming region in what astronomers call the local group, our little neighborhood of galaxies. This nebula is so bright, so energetic, that if it were as close to us as the Orion Nebula, it would actually cast shadows on Earth at night. Imagine that, starlight so intense it creates shadows. The Tarantula Nebula produces massive stars, the kind that burn bright and die young in spectacular supernova explosions. These explosions scatter heavy elements throughout space, the very elements that make planets and life possible. In a way, the Magellanic Clouds are cosmic foundries, forging the materials that future worlds will be made from. The small Magellanic Cloud has its own star-forming regions, though they're less dramatic than the Tarantula. What's remarkable about the small cloud is how distorted it's become. Tidal forces, the same kind that create ocean tides on Earth, but on a galactic scale, have stretched and warped its shape. There are actual bridges of gas connecting it to the large cloud, evidence of their ongoing gravitational conversation. These clouds serve as incredible laboratories for astronomers. They're close enough that we can study individual stars within them, yet far enough away that we can see the big picture of how entire galaxies behave. It's like being able to examine both the trees and the forest at the same time. What we learn from studying them applies far beyond just understanding dwarf galaxies. They teach us about how larger galaxies like our own grow and evolve. Galaxies don't exist in isolation. They're constantly interacting, exchanging material, influencing each other's development. The Magellanic Stream that connects these clouds to our galaxy might eventually feed new star formation in the Milky Way. As this gas drifts inward over millions of years, it could help replenish our galaxy's ability to create new stars. It's cosmic recycling on an unimaginable scale. The Large Magellanic Cloud is massive enough that it's actually warping our galaxy's disk, creating ripples in the outer regions that astronomers can measure. Even these smaller companions can have profound effects on their larger neighbors. It makes you wonder about influence and impact, how even seemingly minor players in cosmic affairs can reshape entire galaxies. The future of these clouds is both sad and beautiful. Over billions of years, they'll spiral inward, eventually merging with the Milky Way completely. Their individual identities will be lost, but their material will become part of our galaxy. This has happened countless times before with other dwarf galaxies. The difference is that the Magellanic Clouds are bright enough and close enough for us to watch the process happening. They're living examples of how galaxies grow through this steady consumption of smaller systems. It's galactic cannibalism, but in slow motion, playing out over timeframes so vast that entire civilizations could rise and fall without noticing any change. From our human perspective, there's something both humbling and comforting about the Magellanic Clouds. If you live in the southern hemisphere, they're just there, part of the natural landscape of night. They've been constant companions to southern civilizations, as familiar as the Milky Way itself. For those of us in the northern hemisphere, where these clouds never rise above the horizon, their absence is a reminder that the universe looks different depending on where you stand. The sky is not universal, it's local. Your cosmic perspective literally depends on your address. These clouds also blur the boundaries of what we consider our galaxy. Are they part of the Milky Way or separate entities? They orbit within our galactic halo. Their gas streams connect to our disk. Their future is to merge with us. Yet for now they remain distinct, their own galaxies with their own structures. The boundary between them and us isn't sharp. It's more like a gradient, a region of interaction and exchange. Perhaps that's a more honest way to think about cosmic relationships in general, not as clear separations, but as zones of influence and connection. The motions of these clouds, their orbits, and the way tidal forces affect them help astronomers understand dark matter distribution in our galaxy's halo. They act like test particles on a cosmic scale, their movements revealing the invisible mass that surrounds us. In studying our neighbors, we learn about the unseen architecture of our own cosmic home. There's something poetic about that, how understanding others helps us understand ourselves, even on galactic scales. The Magellanic Clouds aren't just our neighbors, they're mirrors reflecting back information about our own galaxy's hidden structure. Gravity works like an invisible sculptor, slowly shaping the cosmos around us. When small galaxies drift too close to our Milky Way, they face an uneven pull that changes everything. The side nearest to us feels a much stronger tug than the far side, and this difference stretches these smaller systems into long, flowing trails. These stellar streams, as astronomers call them, are essentially rivers of stars scattered across space. Most remain completely invisible to our eyes, but advanced telescopes can trace their faint paths wrapping around our galaxy like cosmic ribbons. Each stream tells the story of a smaller galaxy being slowly consumed, its stars pulled away one by one over millions of years. The Sagittarius stream stands out as perhaps the most dramatic example we know. What we see today is the remnant of an entire dwarf galaxy that has been circling the Milky Way for billions of years. With each orbit, it loses more of itself, leaving behind great arcs of stars that loop around us multiple times. The original galaxy still exists as a small core, but most of its mass now forms these sweeping trails across the sky. Something profound happens when you consider what this means. These foreign stars, once part of another galaxy entirely, eventually become indistinguishable from our own. They orbit the Milky Way, just like stars born here, yet their true origins remain hidden in subtle clues, their motions and chemical signatures. Not all streams come from entire galaxies. Some originate from globular clusters, those dense balls of ancient stars that seemed indestructible. The Palomar 5 stream shows us how even these resilient structures eventually surrender to tidal forces. Its parent cluster slowly unravels, creating thin ribbons of stars stretching in both directions, like a delicate thread drawn across space. The technology needed to detect these streams pushes the boundaries of precision astronomy. Surveys like Gaia track over 1 billion stars, mapping not just where they are, but how they move through space. This reveals groups of stars traveling together as a family, even when they appear scattered across vast regions of sky. Through this method, astronomers continue discovering new streams, each one a fossil record of past galactic encounters. What seemed like a smooth, uniform halo around our galaxy now appears as an intricate tapestry of overlapping streams. Each thread represents a different merger, a different story of cosmic consumption. The implications reach far beyond simple galactic archaeology. These streams serve as sensitive probes of invisible dark matter. If space contained only visible matter, streams would follow predictable, smooth paths. But when dark matter clumps exist, they bend and distort these stellar rivers. By studying how streams deviate from expected orbits, scientists can test theories about dark matter's true nature and distribution. The stars within these streams carry their own signatures. They tend to be old and metal-poor, consistent with formation in smaller, less evolved galaxies. Their presence confirms that the Milky Way grew through countless small meals rather than a few large ones. This process of gradual accumulation shaped not just our galaxy's size, but its entire character. The scale of these structures challenges imagination. Some streams stretch tens of thousands of light years, wrapping around significant portions of the galaxy. Picture rivers of stars flowing through space, sometimes intersecting with each other, creating a complex network invisible to casual observation, but fundamental to our galaxy's structure. Living within the galactic disk, we rarely glimpse these streams directly. Yet their existence reminds us that galaxies are not island, they're porous systems, constantly interacting with their surroundings, growing through encounters rather than existing in solitude. This cosmic cannibalism raises fascinating questions about identity and boundaries. When does a star stop belonging to its original galaxy and start belonging to ours? Once stripped from their parent system, these stars become gravitationally bound to the Milky Way. The streams blur the distinction between native and foreign, between inside and outside. The process continues today. The Magellanic Clouds already show signs of tidal stripping, suggesting that future streams will form from these neighboring galaxies. Eventually, when the Milky Way merges with Andromeda billions of years from now, that collision will create even more spectacular streams across the combined system. For astronomers, stellar streams represent a perfect marriage of history and physics. They preserve evidence of ancient encounters while simultaneously testing our understanding of gravity, dark matter, and galactic evolution. Each newly discovered stream adds another piece to the puzzle of how galaxies form and grow. From a more philosophical perspective, these streams expand our concept of home. The night sky contains stars that were never born in the Milky Way, yet now belong to it completely. Our galactic home includes not just the obvious disk and central bulge, but all the scattered remnants of consumed neighbors. This realization suggests something beautiful about belonging. Home isn't necessarily about where you originated, but about where gravity eventually brings you. Stars torn from their birth galaxies find new orbits, new purposes, becoming integral parts of a larger whole. The study of stellar streams also challenges our desire for clear boundaries. If the Milky Way constantly absorbs material from its surroundings, if its edges are defined by ongoing interactions rather than fixed limits, perhaps the question of where our galaxy ends becomes meaningless. Instead of thinking about edges, we might consider gradual transitions, regions where the Milky Way slowly fades into the broader universe. This perspective transforms our understanding of cosmic structure. Galaxies become less like distinct objects and more like processes, constantly changing through interaction and growth. The streams of disrupted stars serve as visible evidence of this dynamic nature, proof that even on the largest scales, the universe remains restless and evolving. Our galaxy reveals something profound about the nature of boundaries in the universe. When we look up at the night sky, we see this bright band stretching across the darkness, and it seems so clearly defined. Yet this appearance, this sense of something with edges, is really just a trick of our limited perception. The human mind craves clear definitions, sharp lines that separate one thing from another. We build our understanding around borders, around the idea that everything has a beginning and an end. But the Milky Way operates by entirely different rules. It doesn't respect our need for neat categories. Scientists often quote a figure of about 100,000 light-years as the galaxy's diameter. This number appears in textbooks, gets repeated in lectures, becomes a comfortable fact to hold on to. But this measurement only captures the bright disk of stars, the most obvious part of our cosmic home. It's like measuring a city by counting only its tallest buildings, while ignoring the sprawling suburbs that fade gradually into countryside. The reality is far more complex, far more beautiful in its ambiguity. Beyond that bright disk lies the stellar halo, a vast spherical region populated by ancient stars and globular clusters. These stellar citizens extend the galaxy's reach to perhaps 200,000 light-years, maybe more. They're the elderly residents of our cosmic neighborhood, having witnessed billions of years of galactic evolution. Then we encounter something even more mysterious, the dark matter halo. This invisible component, detected only through its gravitational effects on visible matter, stretches the galaxy's influence to staggering distances. We're talking about hundreds of thousands of light-years, possibly approaching 1 million. At these scales, something remarkable happens. The Milky Way's dark matter halo begins to merge with that of Andromeda, our nearest large galactic neighbor. This overlap means that in a very real sense, our galaxy is already touching Andromeda, already beginning a merger that won't be completed for billions of years. The collision we anticipate in the future has, in some ways, already begun. It's happening not with the dramatic violence we might imagine, but through this gentle, invisible embrace of dark matter. The story becomes even more intricate when we consider gas. The interstellar medium fills the spaces between stars, but beyond that lies something called the circumgalactic medium. This is a vast envelope of hot, diffuse gas surrounding the entire Milky Way. We can't see it directly with our eyes, or even our telescopes, but we know it's there because it absorbs light from distant quasars, creating a shadow that reveals its presence. This gas extends for hundreds of thousands of light years in all directions. It might contain as much mass as all the stars in the galactic disk combined. If this gas counts as part of our galaxy, then the Milky Way is far, far larger than most people imagine. Each of these components, stars, dark matter, gas, creates its own definition of where the galaxy ends, but none of them creates a sharp boundary. Instead, each fades gradually into the cosmic background, like sound fading with distance until it becomes indistinguishable from silence. This gradual fading reflects something fundamental about how galaxies form and evolve. The Milky Way didn't appear fully formed. It grew through countless mergers with smaller galaxies over billions of years. Each merger added new stars, new gas, new dark matter, but also blurred the boundaries further. Right now, we can observe this process happening. The Sagittarius dwarf galaxy is being slowly torn apart by the Milky Way's gravity. Its stars are being stretched into long streams that wrap around our galaxy like ribbons. Some of these stars have already been scattered so widely that they're indistinguishable from the Milky Way's own stellar population. At what moment did these stars stop being part of Sagittarius and start being part of the Milky Way? There's no clear answer, because there was no single moment of transition. It's a gradual process, like water slowly soaking into soil. The same thing will happen in reverse with the Magellanic Clouds. These two small galaxies are spiraling inward, destined to be absorbed by the Milky Way over the next few billion years. Their stars will eventually become our stars. Their gas will fuel new star formation in our disk. The boundary between us and them is already becoming meaningless. This fluidity of galactic boundaries challenges our everyday understanding of objects and identity. We're accustomed to things having clear edges, definite extents. A table has edges, a house has walls, even the Earth has a surface. But galaxies operate more like weather systems, like atmospheric phenomena that blend gradually into their surroundings. The comparison to Earth's atmosphere is particularly apt. If you travel upward from the surface, the air gets thinner and thinner, but there's no sharp line where atmosphere ends and space begins. Molecules of air extend far beyond what we typically call the atmosphere's edge. They become increasingly sparse, but they never completely disappear. Galaxies work the same way. Stars become sparser with distance from the galactic center. But some stars exist in the halo far beyond the main disk. Gas becomes more diffuse, but it never entirely vanishes. Dark matter's density drops, but its gravitational influence extends indefinitely, growing weaker but never reaching zero. This realization transforms how we think about cosmic scale and structure. When we say the Milky Way has a certain size, we're really making an arbitrary choice about where to draw a line that doesn't actually exist. It's like trying to measure the exact length of a coastline. The closer you look, the more detail you find, the more complex the boundary becomes. Different astronomical purposes require different definitions of galactic size. For studying star formation, you might focus on the bright disk. For understanding galactic dynamics, you need to include the dark matter halo. For tracing chemical evolution, the gas distribution matters most. Each perspective reveals a different aspect of the same cosmic entity. This multiplicity of valid definitions reflects something profound about the nature of reality itself. Objects in the universe aren't really separate, discrete things. They're concentrations of matter and energy within a continuous field. Galaxies are like whirlpools in a vast cosmic ocean, regions where material has become denser and more organized, but still connected to the surrounding medium. The Milky Way exchanges material constantly with its environment. Gas flows in from the intergalactic medium, fueling new star formation. Other gas gets expelled by stellar explosions and winds, carrying heavy elements back into space. The galaxy breathes, in a sense inhaling and exhaling matter across cosmic time. This breathing connects our galaxy to the broader universe in ways that make the concept of edges almost meaningless. The carbon in your body might once have been part of the intergalactic medium. The oxygen you breathe could have been forged in a star that formed from gas expelled by the Milky Way billions of years ago, and then fell back in. These connections extend beyond our immediate galactic neighborhood. The Milky Way sits within something called the local group, a collection of galaxies bound together by gravity. But even the local group has fuzzy boundaries. It's part of a larger structure called the local supercluster, which is itself part of an even larger web of cosmic structure. At the larger scales, the universe resembles a vast network of filaments and nodes, with galaxies strung along dark matter scaffolding, like lights on a cosmic web. The Milky Way is just one node in this network, connected to its neighbors by invisible threads of dark matter and visible streams of gas. This web-like structure emerged from tiny fluctuations in the early universe, regions that were slightly denser than their surroundings. Over billions of years, gravity amplified these differences, pulling matter together into the first stars, the first galaxies. The boundaries we observe today are really just the current state of this ongoing process of cosmic evolution. Understanding galaxies as nodes, rather than islands, changes how we think about our place in the universe. We're not inhabitants of an isolated cosmic city, but residents of a neighborhood that's intimately connected to its surroundings. Our galaxy's history is written in the streams of stars torn from smaller neighbors. Its future is tied to the approach of Andromeda and the expansion of space itself. This interconnectedness extends to the very atoms that make up planets and life. Heavy elements forged in stellar cores get dispersed by supernovae, mixing with the interstellar medium, crossing galactic boundaries, seeding new generations of stars and planets. The elements essential for life have traveled vast distances, crossed numerous boundaries, participated in countless cycles of cosmic recycling. In this context, asking where the Milky Way ends becomes almost philosophical. It's like asking where a river ends when it flows into the ocean. There's a practical answer for navigation purposes, but the water itself continues its journey, mixed now with the larger body, but still part of the same global circulation. The fuzziness of galactic boundaries also reflects the fundamental quantum nature of reality. Even at the smallest scales, particles don't have precisely defined positions. They exist as probability clouds, more likely to be found in some regions than others. Galaxies, in a way, are just vast probability clouds of stars, gas, and dark matter, more likely to contain material near their centers, less likely at their edges, but never dropping to exactly zero probability anywhere in the universe. This quantum fuzziness becomes a cosmic principle, a reminder that nature operates through continuity rather than sharp distinctions. The categories we use to understand the universe: galaxy versus intergalactic space, star versus planet, life versus non-life, are useful approximations, but they're ultimately human constructs imposed on a reality that flows seamlessly from one state to another. About 4.5 billion years from now, our galaxy will experience something extraordinary. The Andromeda galaxy, that faint smudge you can barely see in the night sky, is racing toward us at roughly 110 kilometers per second. This isn't just any galaxy, it's the most distant object visible to your naked eye, sitting about 2 million light-years away. Yet in the grand scheme of cosmic distances, Andromeda is practically our neighbor. The word collision might make you think of a catastrophic crash, but galaxy mergers are surprisingly gentle affairs. Think of it more like two clouds of fireflies slowly drifting through each other. Stars are separated by such enormous distances that they almost never actually collide. Instead, gravity does all the work, pulling and stretching both galaxies into new shapes over billions of years. What's fascinating is that this collision has, in a way, already begun. The dark matter halos surrounding both galaxies are already touching, already starting to blend together. We think of galactic boundaries as clear lines, but they're more like the edge of a forest, where trees gradually thin out until you're not sure where the forest ends and the meadow begins. When Andromeda makes its first close approach, it will dominate our night sky, appearing much larger than our own Milky Way does now. The gravitational dance will create spectacular tidal tails, long streams of stars stretching across space like cosmic ribbons. These aren't just theoretical. We can see similar features in other colliding galaxies throughout the universe, frozen moments in their own billion-year transformations. After that first encounter, both galaxies will swing apart like cosmic partners in a slow waltz, only to be drawn back together by gravity's relentless pull. They'll approach and retreat multiple times, each pass bringing them closer as they lose energy to the gravitational friction. With every dance step, their spiral arms will become more distorted, more chaotic. Eventually, after several billion years of this cosmic choreography, the cores will finally merge. Computer simulations suggest the result will be a giant elliptical galaxy, sometimes playfully called Milkomeda or Milkdromeda. A Milkdromeda. The elegant spiral structures we know today will be gone, replaced by a more rounded, somewhat shapeless collection of stars. Our sun's fate during this merger remains wonderfully uncertain. Sitting out here in one of the spiral arms, far from the galactic center, it might get flung outward into the galaxy's outer halo, or perhaps pulled inward toward the new merged core. Most likely, it will simply find itself in an entirely different neighborhood, with new stellar neighbors, and a completely transformed view of the cosmos. The night sky of that distant future would be unrecognizable to us. Instead of the familiar band of the Milky Way stretching overhead, future observers might see dramatic arcs of stars, bright streaming tails, and the swelling glow of a merged galactic core. It would be a sky show beyond our wildest imagination. Interestingly, this collision won't destroy star formation. It will actually trigger new waves of it. When gas clouds from both galaxies collide and compress, they'll collapse into brilliant new stars. These starburst events will light up regions of the merging system, creating dazzling clusters and colorful nebulae. Over time, though, much of this gas will be used up or blown away, which explains why giant elliptical galaxies, often formed by mergers, tend to be filled with older stars and have little gas left for making new ones. This transformation from gas-rich spirals to quiet ellipticals represents a fundamental change in a galaxy's personality. Young, active galaxies gradually mature into older, more sedate systems, glowing with billions of long-lived stars, but rarely forming new ones. It's almost like watching a bustling city slowly transform into a peaceful retirement community. Galaxy mergers like this happen constantly throughout the universe. In fact, this is the primary way galaxies grow larger over cosmic time. Our Milky Way has already absorbed dozens of smaller galaxies, leaving behind stellar streams that astronomers can still detect in our galactic halo, like archaeological evidence of ancient cosmic meals. What makes the Andromeda collision special is the scale. This will be the first time our galaxy merges with another giant, rather than simply absorbing a small dwarf galaxy. It's the difference between a large fish eating minnows versus two large fish becoming one enormous fish. The merger will also reshape our entire local group of galaxies. The Triangulum galaxy, our third largest neighbor, might join the collision either before or after the main event. Eventually, we'll end up with one massive galaxy at the center of our local group, surrounded by the remnants of smaller satellite galaxies. Looking even further into the future, over timescales that make the galaxy merger seem quick, this new supergalaxy will gradually drift together with other galaxy groups. The expansion of the universe will isolate our local cluster from others, and eventually our local group itself might collapse into a single, enormous elliptical galaxy. It would be the last visible island of stars in our corner of an increasingly empty universe. There's something profound about contemplating these vast timescales. 4 billion years seems impossibly long from our human perspective, yet the Milky Way itself is more than 10 billion years old. The Andromeda collision is simply the next chapter in a story that began shortly after the universe itself formed. This reminds us that galaxies aren't permanent, fixed structures. They're dynamic, ever-changing processes, constantly growing through interactions and mergers. What we see when we look up at the night sky is just one brief moment in a continuous transformation that spans billions of years. The Great Collision forces us to reconsider what we mean by edges and boundaries in space. When does the Milky Way end and intergalactic space begin? When two fuzzy-edged objects merge, at what point do they become one? Perhaps the question itself reveals our human need to categorize and define things that exist in states of constant flux. In the end, the merger with Andromeda represents both an ending and a beginning. The death of two spiral galaxies and the birth of something entirely new. It's a reminder that even on the largest scales imaginable, change is the only constant, and transformation is written into the very fabric of cosmic evolution. When we think about our cosmic future, there's something almost poetic about how distant it really is. In roughly 4.5 billion years, our galaxy will collide with the Andromeda galaxy. That's such an enormous stretch of time that it makes human history look like a single heartbeat. By then, our sun will be going through its own dramatic changes, expanding into what astronomers call a red giant star. The sun's transformation will happen in about 1 billion years from now. It will grow so large that it might swallow up the inner planets entirely. Earth's oceans will boil away long before that happens, though. The surface will become completely uninhabitable for any form of life as we know it. So in a strange way, the galactic merger might be the least of our planet's worries. But from the galaxy's perspective, this collision will be absolutely transformative. Two massive spiral galaxies, each containing hundreds of billions of stars, will slowly dance together over millions of years. The gravitational forces involved are beyond anything we experience in our daily lives. Stars will be flung into new orbits, some ejected completely into the darkness between galaxies. What fascinates astronomers is how predictable this cosmic choreography actually is. We can measure the velocities of both galaxies right now. We can calculate their trajectories with remarkable precision. The math tells us this merger is inevitable, written into the very fabric of space and time itself. The new galaxy that forms from this collision will be completely different from either the Milky Way or Andromeda. It will likely be more elliptical in shape, rather than the beautiful spiral arms we see today. Astronomers have already given it a name, Milky Way, though that might seem a bit premature given the timescales involved. This brings up something quite profound about identity and belonging. What happens to our sense of home when that home transforms into something entirely different? We attach so much meaning to being part of the Milky Way galaxy. It's where our solar system formed, where every star we see with the naked eye resides, where all of human history has unfolded. When we really examine what a galaxy is, though, the boundaries become surprisingly fuzzy. It's not like a house with walls and a roof. The edges of the Milky Way fade gradually into the space between galaxies. There's no clear line where our galaxy ends and empty space begins. If we focus on the bright disk where most stars live, our galaxy might extend about 100,000 light-years across. But there are much older stars scattered in a roughly spherical halo around that disk. These stars can be found twice or even 3 times farther out, remnants from when the galaxy was much younger and smaller. Then there's the dark matter, that mysterious substance that makes up most of the galaxy's mass. We can't see it directly, but we can detect its gravitational effects. The dark matter halo extends much farther than the visible stars, perhaps close to 1 million light-years in radius. At those distances, it's already starting to overlap with Andromeda's own dark matter halo. Between and around galaxies, there are also vast clouds of extremely thin gas. This circumgalactic medium connects our galaxy to the larger cosmic web, the vast network of matter that spans the entire observable universe. So in a sense, we're already connected to everything else out there. Every single component of our galaxy is in constant motion and change. Stars are born from collapsing gas clouds, shine for millions or billions of years, then die in various spectacular ways. Some explode as supernovas, scattering heavy elements back into space to form new generations of stars and planets. Others fade quietly into white dwarf stars that will glow dimly for trillions of years. Even the spiral arms that give our galaxy its distinctive appearance aren't permanent structures. They're more like waves moving through the disk, temporary concentrations of stars and gas that form and dissolve over tens of millions of years. The arms we see today are completely different from the ones that existed when the dinosaurs roamed Earth. Smaller galaxies are constantly falling into the Milky Way, adding their stars to our collection. We can still see the remnants of some of these ancient mergers, streams of stars stretched across the sky by tidal forces. Each of these events changes the galaxy's structure and composition in subtle but measurable ways. The galaxy starts to seem less like a fixed object and more like a process, a flow of matter and energy that continues over cosmic time. It's a bit like asking where a river ends. Is it at the mouth, where it meets the ocean? Or does it include the entire watershed that feeds into it? The answer depends on what you're trying to understand. This might be the most important insight about our cosmic home. It's not a container with sharp boundaries, but rather a set of relationships and connections that extend far beyond what we might initially imagine. We're part of something much larger and more dynamic than a simple collection of stars. The temporary nature of everything doesn't diminish the significance of our galactic home, though. If anything, it makes it more precious and remarkable. Out of all the galaxies in the observable universe, this is the one that happened to form our Sun, our Earth, and ultimately, us. The Milky Way's lack of clear edges doesn't make it less of a home. It makes it a richer, more interconnected part of the cosmos itself. Where something begins and where it ends, that's always been one of those questions that seemed simple until you really think about it. Take our galaxy, the Milky Way. You might assume it has clear boundaries, like a country on a map, but the reality is much stranger than that. The edge of our galaxy isn't really an edge at all. It's more like a gentle fade, where one thing slowly becomes another thing. Gas clouds drift outward into space, carrying pieces of our galaxy with them. These particles don't suddenly stop being part of us, just because they've crossed some invisible line. Think about the dark matter halo that surrounds our galaxy. This invisible mass extends far beyond the visible stars, stretching out into what we might call empty space. But it's not empty at all. It's filled with matter we can't see, matter that belongs to us in a cosmic sense. The thing is, without this dark matter, our galaxy wouldn't even exist as we know it. The halo holds everything together, like invisible glue binding the stars and gas clouds into a coherent structure. Take away that unseen mass, and the Milky Way would have scattered into space billions of years ago. Gas clouds play their own crucial role in this cosmic dance. They collapse under their own weight, forming new stars, then get blown apart by stellar explosions, only to collapse again somewhere else. This endless cycle of creation and destruction has been going on for billions of years. Heavy elements, the building blocks of planets and life itself, get forged in the hearts of dying stars. When these stars explode, they scatter their contents across space, enriching the gas clouds that will form the next generation of stars. Without this process repeating over and over, there would be no carbon, no oxygen, no iron, none of the elements that make up our world. Our galaxy didn't grow in isolation either. It has neighbors, and those neighbors have shaped its development in ways we're only beginning to understand. The Milky Way has been pulling in smaller galaxies for billions of years, absorbing their stars and gas, growing larger and more complex. Some of these cosmic meals left traces we can still see today. Streams of stars stretch across the sky, the remnants of smaller galaxies that got torn apart by our galaxy's gravity. These stellar streams blur the line between what belongs to us and what belongs to them. The Andromeda Galaxy, our nearest large neighbor, is actually approaching us. In about 4 billion years, the two galaxies will collide and merge into something entirely new. Even now, Their outer regions are starting to interact, their dark matter halos beginning to overlap. This raises a fascinating question about identity and belonging. If particles from Andromeda are already mixing with particles from the Milky Way, where exactly does our galaxy end and theirs begin? The universe doesn't seem to care much about our human need for clear categories. On the largest scales, our galaxy belongs to something called the local group. This is a collection of galaxies bound together by gravity, including the Milky Way, Andromeda, and dozens of smaller companions. The local group itself has fuzzy edges, gradually blending into the larger cosmic web. For astronomers trying to build models and run calculations, defining boundaries becomes a practical necessity. They need to draw lines somewhere, even if nature doesn't recognize those lines. But for the rest of us, the question becomes more philosophical than scientific. What does it mean to belong to something that has no clear edge? Our sense of home usually starts with definite boundaries. A house has walls, a city has limits, a country has borders, but the cosmos operates differently. We belong to Earth, but Earth belongs to the solar system. The solar system belongs to the Milky Way, which belongs to the local group, which belongs to larger and larger structures stretching across the observable universe. Each level of belonging is real and meaningful, but none of them has a final boundary. The particles that make up your body were forged in ancient stars, scattered by supernovas, gathered into new solar systems. In a very literal sense, you are made of galaxy stuff. Your atoms have been on a cosmic journey, lasting billions of years. Even now, that journey continues. The galaxy rotates slowly, carrying our solar system around the galactic center, once every 220 million years or so. We're all traveling through space together, passengers on a cosmic carousel that's been turning for longer than life has existed on Earth. The spiral arms we see in pictures of other galaxies aren't permanent structures either. They're more like waves moving through the disk of stars and gas. Material flows into the arms, gets compressed, forms new stars, then flows out again. The pattern persists even as the stuff making up the pattern constantly changes. This constant motion and change means that the galaxy we see today is different from the galaxy that existed a billion years ago. It will be different again a billion years from now. Galaxies evolve, just like living things, but on timescales that dwarf biological evolution. The invisible parts of our galaxy might be the most important parts of all. For every star we can see, there's roughly 5 times more mass hidden in dark matter. This unseen component shapes the galaxy's structure and evolution in ways we're still trying to understand. Gas clouds far from any stars are quietly preparing for future generations of star formation. When conditions are right, these diffuse regions will collapse and ignite, creating new stellar nurseries. The galaxy regenerates itself through these cycles of birth and renewal. Sometimes we think about cosmic distances and feel small, insignificant in the face of such vastness. But there's another way to look at it. We're not separate from this cosmic machinery, we're part of it. The same physical processes that shape galaxies also shaped the conditions that allowed life to emerge. The gradual blending of one cosmic structure into another reflects something deeper about the nature of reality itself. Sharp boundaries and clear categories are often human constructs, useful for organizing our thoughts but not necessarily reflective of how the universe actually works. Connection and continuity seem to be more fundamental than separation and isolation. Every level of cosmic structure, from planets to galaxy clusters, exists in relationship with other structures. Nothing stands completely alone. The boundaries we think we see around us, they're really just tricks of perspective. When you look at your hand right now, where does it actually end and the air begin? The atoms at your skin's surface, they're constantly exchanging particles with the atmosphere around you. Every breath you take brings in molecules that were once part of distant stars, and every exhale sends pieces of you out into the world. Scientists have discovered that the human body replaces most of its cells every 7 to 10 years. The calcium in your bones today, It came from ancient ocean creatures. The iron in your blood, it was forged in the heart of a dying star billions of years ago. You're literally made of cosmic dust, rearranged into this temporary pattern that thinks it has clear edges. But the blending goes deeper than that. Your electromagnetic field extends far beyond your physical body. Every heartbeat creates electrical waves that can be measured several feet away from your chest. Your brain generates magnetic fields that interact with the Earth's own magnetic field. In a very real sense, you're already overlapping with everything around you. Plants and animals do this boundary blending too. Trees in a forest, they share nutrients through underground fungal networks. One tree's roots connect to another's through these microscopic partnerships. When a tree is attacked by insects, it can send chemical signals through the network to warn other trees. The forest isn't really individual trees at all. It's more like one giant organism with many visible parts above ground. Ocean creatures take this even further. Some jellyfish are actually colonies of thousands of smaller organisms working together. Each part has a specialized job. But none could survive alone. The boundary between individual and collective becomes meaningless. Coral reefs work the same way. Tiny animals building massive structures that become home to countless other species. Even at the quantum level, particles don't have definite positions until they're observed. They exist in probability clouds, spread out across space. When two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance, but it suggests that separation itself might be an illusion. The atmosphere doesn't end at some clear line either. It just gradually thins out as you go higher. At what point does Earth's atmosphere become space? There's no sharp boundary, just a slow transition. The same is true for our solar system. Where does it end and interstellar space begin? The sun's influence extends far beyond the last planet, creating a bubble of charged particles that slowly fades into the cosmic background. Galaxies blend too. Our Milky Way is already colliding with the Andromeda Galaxy, a process that will take billions of years. The gravitational dance has already begun, with stars being pulled back and forth between the two systems. In cosmic time, we're already one galaxy, just stretched across a few billion years of slow merging. Light from distant stars has been traveling for so long that some of those stars have already died. When you look up at the night sky, you're seeing the past mixed with the present. Some points of light are stars as they were thousands of years ago. Others are galaxies from when the universe was young. Time itself becomes blended across space. Your body is mostly empty space too. If you could shrink down to see individual atoms, you'd find that they're almost entirely nothing, with tiny particles buzzing around vast empty regions. The feeling of solidity comes from electromagnetic forces, not actual matter touching matter. You're more like a cloud of energy than a solid object. Water cycles through everything, connecting all life across time and space. The water in your cells has been rain, rivers, oceans, ice, and vapor. It's been inside dinosaurs, ancient trees, and other humans throughout history. Every drop connects you to every other living thing that has ever existed on Earth.